we have to take some time and we have to enter into deep dive discussions. We have to really put in our mind, heart, and soul to think that what is the best way by means of which we can help India to make use of the big sand mineral or the primary resource, or what are the best ways by means of which we can really extract the rare earth metal values. I think very, very coherently or very, very relevantly, you have given the title as ore to product and recycling. So number one is from the ore, how best you can extract the mineral value. And second thing is after you just extract it, be it in the form of rare earth oxide, then you have to convert it into rare earth. Then I think you can put it in the different forms. As all of you know, these rare earths are finding their applications in catalysis, glass industry, magnets, even coatings, thermal barrier coatings, polishing, batteries, capacitors, additives, alloy preparation, pass. Then we can, I can keep on telling you a big list. But in nutshell, I'll tell you, for any country, four things are very important. One is its strategic sector. Second one is its industrial sector. Third one is its domestic sector. And the fourth one is its very, very socially relevant consumer as well as the other market needs. So as far as rare earths are concerned, I think they're finding their application in all the four different parameters that I discussed with you. If you just take the strategic sector again, whether it is related to aerospace or whether it is related to military applications or whether it is related to even advanced ballistic proof and ballistic applications, these rare earths are finding their applications to a huge extent. Therefore, for India, by India, I think we have to really make these rare earths as a much more relevant component for Indian economy. I think very recently, US and India, we had a very special meeting. It is called India-US 2+2 meeting. Two leaders from India, the Honorable Minister Jaishankar and the another Honorable Minister Rajnath Singh. These two ministers from India and from the US side, we had one Mr. Anthony, the other one Mr. Lloyd Austin. So this 2+2, this particular combination, they had a very deep dialogue and they focused their attention on one particular topic, that how best the supply chain resilience could be really brought in with much more effective manner in the whole globe. Because now we are living in a totally different situation. The geopolitical situation, especially US-China relationship, it is giving a lot of new nuances. It is giving a lot of new risks or new threats. I would say they are opening up new avenues also as far as the supply chain is concerned. If you just consider the rare earth related supply chain, today China is dominating 90% of the rare earth related supply chain. But India being the fifth largest reservoir, India having an Indian economy of $200 billion for rare earth, why we are not able to do that? Why we are not able to come up with our own supply chain? What is the problem with respect to the indigenous supply chain formation? So end-to-end supply chain strengthening is the need of the hour. I think this is where we, the research organizations and industries, we can put in our hands, put in our efforts, put in our minds and ideas by means of which we can come up with a kind of a very great and a successful formula by means of which we should make the country really to feel proud. And this one particular operation, which I told is upscaling of upstream as well as downstream activities related to rare earth elements, I think we can make India as a very strong power and we can make India as self-reliant India in the upcoming days. I think that should be the motto of today's program. So let us all put in our ideas and interest in this particular direction of making India as self-reliant in the field of rare earth also, by means of which we all can really feel proud that we are no longer depending upon anybody else in the global market. We may take maybe 3 years time, 5 years time, or at the max 7 years time. And we have to take it as a challenge that within another 5 years or 7 years, we will make India as a very self-supporting and a self-reliant India in the field of rare earths, by means of which all our important requirements, critical, less critical and highly critical requirements by means of our own reserves and our own technologies. Let us take that as the motto of today's discussion. And I wish today is going to be a great day. It is going to give us a new learning curve. New options are to be opened. With this kind of positive remarks, I also look forward to listen to each and every one of you. I'm very happy to be a part of this inaugural event of this iConnect of today's event. And I wish this event every success. And I wish in Indian industries and CSIR labs, we will handhold, handshake, and we will continue our relationship till we achieve the goal which I mentioned. Have a wonderful day. Thank you very much for the opportunity.
Uh, Madam, thanks for providing us the tone of the today's session. Actually, just now it provided us entire like how rare earth are very critical to us, and what we can look forward from this iConnect meeting, and what is that we have in the future as a vision in terms of rare earth in the entire value chain. And thank you very much for giving us a illustrative and comprehensive view of the entire iConnect. So thank you very much. May, thank you, thank you, thank you. Thanks for your time also. So, maybe I will start my first request to Dr. Professor Kali Sanjay. He's head of extractive metallurgy, hydrometallurgy division at IMT Bhubaneswar. He has close to 30 years of experience in the field of extractive metallurgy. He has more than 40 papers and 3 national patents. And he is one of the national well-known experts in the field of rare earth extraction. And we are looking forward to you, sir, and for providing us a uh, uh, yeah, entire overview of rare earth extraction from primary and secondary resources. And the floor is open to you, sir. And before I start, there is a small thing I wanted to tell. And due to a last minute urgent meeting which is scheduled with his headquarters, Dr. B.R. Mishra, DGM IRL is unable to join. He was the one who was calling a couple of minutes ago. So he is in IRL headquarters. He is unable to join, and he has shared his regrets. So I am also really sorry that we could not have a presentation from him. And we will just continue with the flow. So the floor is open to Professor Dr. Kali Senji, and we look forward to all other speakers also. Thanks to everybody for your attention. Thank you. Thank you. Sir, please.
Yeah. Thank you very much. Are my slides visible?
It is visible, sir. It is visible.
Thank you, Director Sipri and the team iConnect for inviting me. And I'm going to start with a brief introductory, maybe a startup this thing. So I just covered a little bit on the fundamentals of rare earth and where we want to utilize, and then why there is a need. So if you see the rare earths, basically we all know it. Basically, we have the lanthanide series, so it will start from here, and there are 15 of them here, and then there are classified into light rare earths. So you have lanthanum to samarium; these are called the light rare earths, and the rest of them are heavy rare earths. And we have one extra here, the yttrium, though it is lighter than the light rare earths, but it comes always with the heavy rare earths, therefore it is always classified as a heavy rare earth. So you have a total 15, 1, 16, and also there is a issue here where the scandium is also considered. Mostly scandium comes along with the rare earths, and therefore the applied chemistry, the Union of Pure and Applied Chemistry has actually included the scandium in the rare earths. So rare earths are not actually rare because they are plenty available in the earth crust, but they are very distributed, and then they are very difficult to techno-economically extract. That's why they are called rare. And the most of the focus for these rare earths were by defense, and it was not being considered as a common man's requirement. And like you can see on the right side, you have the lanthanum going for night vision goggles, ND going for laser find ranges, europium, erbium, samarium, and all these things are used for defense. So they were mostly used for special purposes. and it was mostly developed by the defense or strategic sectors for a small quantity and irrespective of the techno-economics, and they were used for different purposes. But the things have changed lately, and we are into the developmental goals, basically green energy. So when we're talking about green energy, the REs are finding a major role. So first thing is the permanent magnets that are required for the windmills. They use a huge amount of NdPrs and kind of materials in the magnets. And you have the EVs coming out where they have the large requirement of rare earths, and then also the phosphors for the lighting. So these general developmental goals have included rare earths, and therefore they became a critical requirement for economical growth also. Now, once this became an economical issue, then the techno-economics came into play, and people have started looking into the processes which are technically viable and also economically feasible. So if you see the world production and then how the mapping was gone earlier stages, USA, the blue one is United States. They also have a good amount of the rare earth resources, primary resources. They were having the rare earths extraction, but at later stage, somewhere in between 2003 onwards, the China has started supplying cheaper REs to the market, and therefore the US has closed their operations. And then there is an embargo, but the China has started restrictions on export of rare earths somewhere here. And then the other people also started looking into, and the US countries like US, they reopened, and Russia is and Australia is also coming up, and there is a substantial increase in the rare earth production by other countries also. And India is also part of this scheme where we are also looking for the improving our indigenous production of rare earths, and this is all in rare earth oxide equivalent in metric tons. Now, there are some data which I have taken from the net. We have our IREL, which produces basically rare earth oxides, and then we have a monazite in India. We stand about 10.2 million tons. The production of rare earths from monazite is about 2,700 tons per year, and currently IRE also producing about 7,700 tons per year. But these are all from the primary resources, monazite, Indian monazite from Indian beach. But we also have an opportunity, as Ma'am Kalesal has also mentioned, that we need to look into opportunities where the recycling is one important thing that is catching up. So many times we buy the final product, what she was mentioning, final product into the country. Now you utilize it, and the end of the life has reached. And that's the point when you have to start looking for getting back instead of scrapping it and selling it to the other places. So therefore, the REs is a good extraction from recycling is a good opportunity. I'm going to give some couple of examples that the CSRMT has done, and this is not just a end of the list of these things, but these are some of the things that we have done, and this just gives an idea about how we can go forward. So one of the important raw material could be the permanent magnets, which have been used for the windmills or any kind of audio systems and those kind of straps, machine strap, and the nickel metal hydride batteries from hybrid cars. And you have a phosphorus in the fluorescent lamps or flat panel displays. And we're also looking for something very strategically from fly ash and bauxite, which I will be covering in this presentation. So coming to the magnets, so for example, if you take any boron magnet, you have a Nd about 30%, and you have a boron about 5%, and there will be some impurities. So there will be these magnets or all these resources will not be exclusively RE content, but RE is a part of the system. So you will be having an issue of separation of impurities and then selectively getting these materials and then final products. And here somewhere cobalt magnet, you have 41% cobalt, 59%. Cobalt is another strategic important critical metal for India. And nickel metal hydrides, again, nickel, lanthanum, cerium, and phosphorus, you have yttrium, europium, lanthanum, cerium, and terbium. So I'll just briefly describe about the kind of flow sheets that can be utilized for using these secondary resources. So one issue that main thing will come is the scrap sizing. So especially when you have a magnetic, very highly magnetic ND magnets and all, the issue comes whether how do you pulverize it. but there are some means of doing it, and then we can get the size reduction. Once you have size reduction, so the general scheme is, these are general schemes where mostly it is done by hydrochloric acid leaching, and then there will be impurity removal. For example, in this case, iron is removed by lime addition, and then you have a filtrate, which can go for different routes for downstream processing. In this case, the NdPr were extracted by solvent extraction, and boron was left in the raffinate. And here we used a DEFA, and then we have two options. One option is that you can use for oxalic acid for a stripping of the loaded organic from the loaded organic, and we can have a mixed oxalate of NdPr, and then we can have produce a mixed oxalate, or we can also strip it with sulfuric acid in case we want to have the end products in a sulfate form. So there is a crafting, there is a process where you basically, the size reduction is the primary unit operation, then you go for or separation sometimes, and then you go for a leaching. Leaching could be a selective leaching, and then you have a series of unit operations where you purify it, and then those can be chemical methods, or methods like ion exchange or solvent extraction, and end products can be metals of your need. So similarly, samarium cobalt we have done for grinding. Again, we went for two routes. One is hydrochloric acid, where we have leached the values, and then we used again DEFA to have a precipitated, the strip was precipitated by oxalic acid and calcine to produce the samarium oxide. The other route could be a sulfuric acid, straight away leach it and precipitate oxalic acid in this one. So whenever we use the solvent extraction, because though it is a capital intensive, the product will be of high purity. In this case, we will be expecting about 99.9% pure samarium oxide, while without solvent extraction, you still can get a simple flow sheet about 98% purity. So that's an issue where you need to weigh about the SX requirement, whether the capex is intensive or the purity versus purity. So it's just a representation. So you have a magnetic strap, you go for a leaching liquor, you have a strip solution of RE sulfate or RE chloride, or you can have a mixed oxalate, and then you can have this RE mixed oxide after calcination. Now, other way, you can get directly, for example, in this case, when we separate the cobalt, you can directly from the chloride media, you can produce the cobalt metals, or because cobalt chloride media, metal production of cobalt is tricky. So people also go for oxalate and also produce the cobalt oxide, which can be directly used for lithium-ion batteries kind of requirements, or you can from there also you can produce the cobalt metal. And this is the flow sheet for nickel metal hydride, where the metal hydride is crushed, grinded, and then we use the sulfuric acid, and selective precipitation of RE was carried out using oxalic precipitation route, and then they were calcined, and here we have separated the nickel, which went for nickel production. And we are also been working on the recovery of 5 REs. Basically, the phosphorus contains about 45 to 50% of REs. These are the tube white content. You can see that when you remove that white content, which is in the spent tube light, so you'll get the phosphor. So it will have about yttrium 30 plus percentage, lanthanum, cerium, and terbium. We have a two-stage leaching process. Initially, we leached with sulfuric acid to get yttrium and the EU, and then followed by the HCl leaching for getting the lanthanum, cerium, and terbium. So this process is also we have developed using the secondaries. Now, coming to the strategic sector, so we are looking for the recovery of rare earths from Indian fly ash. The Indian fly ash contains about 450 ppm to as high as 2000 ppm of REs. So if you see the difference between the fly ash of China plant and Indian plant, China's fly ash contains more alumina. It's about 35 to 40 plus percentage of alumina, and they don't have a bauxite resources. So alumina recovery can be one aspect that they will be looking into. But in our case, we have bauxite resources, and having a low alumina content of 25-28% may not be feasible just to recover alumina. So we developed a process where we broke the matrix. Basically, it is a mullite form, And silica, which is about 60 to 60%, is basically 50% in amorphous form, 50% in quartz form. So first we broke the matrix by dissolving the amorphous form of silica, that is 30% of the silica comes here. It can be produced as a sodium silicate or reprecipitated to produce calcium silicate, which is a product from which we can make all these products. Or in this process, we can also regenerate sodium hydroxide, which can go for alkali leaching process. Basically, there are two products, sodium silicate or calcium silicate from the 30% of the silica. And then we go for sulfation roasting followed by water leaching, where we reject the quartz bearing residue that contains most of this silica, and undissolved alumina. Sometimes alumina is present in alpha alumina, which cannot be broken because it's a mullite form, and that stays back in the impure quartz. And then we have a liquor containing alumina and iron content mostly, and also we have various other impurities. So we precipitated out selectively high pure alumina and rejected all the impurities into the iron hydroxide. So this quartz bearing residue, which is having about 95 plus silica, can be used for building materials like this, because having alumina for alpha alumina, it may not be useful for the transparent glass, but it can be used for building blocks, glasses for building materials. So we have taken care of silica, we have taken care of alumina, and we thought this is iron hydroxide can go for red oxide paints and pigments. And interestingly, what happens is that if you see the REs which are present in the initially about 453 ppm are basically enhanced and then concentrated into the iron hydroxide residue. So instead of 15 ppm, the scandium became 111 ppm. So instead of 1 ton fly ash, we can start here with a small portion of this one, which is about 65 kgs of iron hydroxide. We can produce this 200 grams of REs. Now, if you see the mapping, which is a recent publication by some other team, they have mapped the Indian coal fly ash, and then they found that what we have started with is the 453 ppm, which is somewhere around this lower region. But there are, if you go to Lignite Corporation, Tamil Nadu, and lignitic coal, you have REs as high as 2000 ppm. So therefore, the process can be adopted for many of these Indian coals, which have a good amount of REs. And what we are working is also at the bottom level, which is about 453, which is more or less at the lower level. So the taking this clue that we also took an initiative to look for extraction of rare earths from bauxite residue. Basically, bauxite residue is the residue coming out from leaching of bauxite by alumina industries, refinery industries. And it is kind of hazardous because of alkalinity pH about 11 and need to be stored with full lining and without a leakage to avoid ground contamination. And India produces about 10 million tons per annum, and there is a serious necessity to look for the utilization of this red mud, which is being utilized only 15%. Though fly ash is being utilized for many applications, red mud is not that much being utilized because of its high alkalinity. So in the same holistic method, the way we have concentrated, because you cannot attack the REs from the beginning, you need to take the major mass out, concentrate the RE into a smaller mass, and then attack it. And you cannot produce, when you're talking about waste, another waste, because that is not a solution. So we need to completely, like the fly ash process, where we don't have even a residue. We just broke the matrix into the 4 parts, and then 4 parts have complete utility. Similarly, we wanted to have a holistic utilization of red mud, and here we have organizations like NML, IMMT, and Jawaharlal Nehru Aluminum Research Development and Design Center, JNRDGC. We all came together with all aluminum industries, major industries, NALCO, Hindalco, and Vedanta. We signed an MOU. And basically, if you see here, it's a similar kind of material. We have an alumina, we have iron here more. The fly ash has only 4% to 6%, but we have high iron content. But where is interesting, we need to extract also TiO2, and we have REs. Here, the RE is much high, like compared to fly ash, where 15 ppm initial, we have a 50 to 60 ppm of scandium. So initial studies are being carried out by JNRDC for silica upgradation if there is a possible. And then NML follows, in 2 different flow sheets are being followed. NML goes for first getting the alumina followed by the alumina iron removal, and then chemical treatments are to separating the titanium dioxide and from the concentrate RE extraction. IMMT is actually basically for going for reduction roasting, magnetic separation. We are separating the mag fraction and then sending it to NML for the electric arc furnace to produce the pig iron. And the non-mag fraction, we are taking it, going for salt roasting and water leaching, to followed by chemical treatment to produce titanium and RE. This is the ongoing project, and some interesting results have already come, and we are going ahead with this. And another area that we are looking for is basically we can produce many of these REs from different sources, be it from B sand or from secondary sources. We can produce up to oxides, chlorides, and phosphates. But there is a gap where these oxides have to be converted into the metal before they can be further utilized. For example, in case of magnets, you need an Nd metal, so you can't have an Nd2O3 to start with. So this technology is being carefully safeguarded by many countries, and especially China had this since 1965 onwards. So they are not allowing this technology to go out. And we have a lot of people worldwide, people are trying for, and then we have different processes. For example, in case of earlier stage, it was a calciothermic reduction process where SICRI is also involved in producing calcium metal to BRC for the further production. And we have a fluoride electrolysis and then oxide electrolysis. In this case, the most of the European Union, even last year, a few years back, 2015, the whole of Europe has come together, RE for EU, and they joined, and then they produced the 1 kiloampere cell of Nd in a fluoride process. Fluoride route is known to be economically viable, though other processes have their own advantages. I'm not going into controversy about the discussion about those which are bad and good, but all this needs to be done. And then in CSR IMT, we are looking for a 3 kiloampere cell of a fluoride through fluoride route, which is the base commercial level of production of Nd metal, which can be taken up to the industry. Now, coming to little bit economics. Now, when we talk about rare earths, very interesting part is, okay, rare earths is anything rare earths. No, it's not like that. A recent paper, I just took it from the recent paper. If you see here, when we take any of the resources, especially, we get a large mass from lanthanum and cerium and this kind of rare earths. But if you see the right side, which is the economical value, they are very small amount. So what will happen here is that when we also go for rare earth extractions, we get a mixed rare earths, and then we go for a large amount of money, we spend it for separation, and the major mass is actually occupied by the low quality REs. But the things are changing where cerium, lanthanum, which are higher in mass but lower in the value, are also getting, for example, this recent demand which shows that aluminum alloys with lanthanum and cerium can actually bring down the casting, the foundry costs, and then a lot of changes in the downstream process of production. So production costs, they are giving the alloys, and this is expected to save like 2055. There is a huge energy which is going to be saved because of using REs such as low-cost REs like cerium and lanthanum in aluminum alloys for the production. So if you see here, you go for terbium and all those things for the first one, the extraction. The sequence goes for second one is for the ND and for magnets. And then you have a 70% of that cerium and lanthanum. So once these all things can be utilized, the economics will. But still, even without these things also, the having said this, you need to have the NdPr, Nd, and then we also need the REs for the LEDs and all kinds of electronics which we require. So the economics is changing and significantly, and we cannot just tell that they are low quality REs anymore. And then we should look for all kinds of RE extraction wherever it is possible, be it a secondary, low grade, or any kind of resources that are available in the country. So in concluding, identifying tapping secondary resource in the country can be an option, good option for rare earths. process engineering techno-economics plays a vital role because now we are not looking for a defense application. We are looking for a techno-economical applications, and therefore economics is a vital role, comes into vital role. And scale up. Scale up is an issue which we need to be careful. Not doing it in a small scale and demonstration. We need to go for a commercial level to implement and see that the nitty-gritties are there. And CSRMT has been actively involved in for the extraction of strategic metals like cobalt, nickel, and from deep sea nodules and all kinds of resources. We are also into that areas, and we look forward for all the CSL labs or anybody in the country that we can join hands and then develop these technologies. And we have been awarded for the fly ash that 2019 we got the Grand Fly Ash Utilization Challenge. Thank you very much, and I thank Director City for giving an opportunity. I thank our director and the staff who have actually worked in this all this work that I showed, and also some figures and then the numbers that I taken from the public domain is to. Thank you very much.
Thank you very much for your very excellent and opening speech, because that has set the tone for this session. Actually, you have given a very comprehensive perspective of the R&D activity on rare earth extraction. Name any end-of-life product, whether it is samarium, cobalt, NdFeB, phosphorus, or industrial waste such as fly ash, bauxite residue, where you also have a national level consortium, and your attempts to produce ND product, ND metal and light metal alloys. So it was really an illustrative speech, sir. Thank you very much. And also we congratulate for your recent award with from NTPC for the fly ash utilization. Thank you very much for the illustrative speech, sir. Thank you. Thank you. Thanks. Yeah. So please allow me to proceed to the next speaker, Dr. U. Rambabu. Dr. Rambabu is working as a senior scientist at Cement Hyderabad. He is working in the field of extractive metallurgy for more than 26 years. Before joining Cement, he has had a postdoctoral stints at Taiwan, Japan, and South Korea, and he is having more than 50 papers and 3 patents to his credit. So Professor Rambabu and Dr. Ratish, their team have developed extraction of rare earth from metal values from end-of-life products such as phosphorus and magnets, if I'm not wrong, and they have transferred some of these technologies also. So we will look forward to your illustrative speech, sir. The floor is open to you. Thank you. Sir, your slides are visible. You can please start, sir. You can unmute yourself, sir.
Hello, I am audible, sir.
Yeah, it is audible now, sir. It is audible. Please, sir. Please, you can start, sir.
So I thought that my lecture is after
No, it was supposed
IRL
to be,
lecture.
sir. No,
Okay, sir.
yeah. Dr. Mishra is unable to join due to some urgent commitment from his headquarters.
Okay, sir.
Now we are going with the flow, sir. Yeah. Thank you, sir. Thank you. Thank you.
Okay. So,
I think voice is breaking, sir. I think, sir, there is some signal.
first of all, I would like to thank
Yeah, we can invite next speaker by the time Dr. Rambabu is fixing his system. Jaya?
Yeah, ma'am.
Yeah, we can invite next speaker while he is fixing his system, whatever problem they are having at their end.
Sir, Dr. Rambabu, I mean, there is an audio issue from your side, sir. Hello. Actually, voice is breaking, sir. Hello.
Please go ahead with the next speaker. Dr.
Yeah, sir. Okay, sir. Okay.
So next, Dr. Rambabu will give the next speech. I think that would be ideal.
Okay, sir. Okay, sir. Okay. Thank you, sir. Thank you. Maybe he can withdraw the slides, sir, please.
Jaikumar, I'm ready.
Yeah,
This is
okay, sir.
Jayashankar from NIST.
Yeah, sir, Dr. Rambabu, you can withdraw your slides, sir. Maybe in the next presentation you can have it, since there is audio issue. I think, Dr. Jaishankar, can you please try to upload the slides? Let us see whether it is, or maybe yeah, please. Okay. I welcome Dr. Jaishankar. He's a senior principal scientist at CSR NIST at Trivandrum, and he has close to 20 years of research experience in the field of extractive metallurgy. And I welcome you, sir. And he holds to his record more than 6 national patents and more than 50 papers publications. And the floor is open to you, sir. And we look forward to your illustrative speech on rare earth extraction at NIST. Thank you. Thank you.
Yeah, thank you, Jaikumar. I'm audible now?
Yeah, you're audible now.
Slides are okay. Thank you very much.
Yes,
So
sir.
very good morning to all, and welcome to for this iConnect meeting on rare earth talk. And as I'm Dr. Jayashankar from CSR NIST Trivandrum, and I'll be talking about the activities, especially in rare earth minerals and materials. As you know, the CSR NIST is working in this rare earth based extraction and as well as the material development for last 2 decades. So we have the vast experience on the rare earth as well as the rare earth extraction as well as the rare earth materials development. So as a previous speaker from our CSR laboratory, so they already highlighted about the rare earth usage and other secondary resources extraction. So I'll just give a glimpse. When we start, when the rare earth usage in some time back, so it was very limited usage. Now the rare earth materials are used in many applications, and even the recent like our mobile phones and other updated our devices. So all the electronics equipment now they have started using the some quite amount of rare earth materials. The usage, as you can see, it is from from metals and alloys, catalyst, and as even the automobiles. And other devices and all it started using this rare earth thing. So the rare earth materials are vast application. If you look into the source, so already it was highlighted. So where are the source of rare earths are present? So as you see in natural mineral rose, this is available with the phosphates, silicates, and carbonates and oxides. And because these metals are occurs in various geological deposits all over world. In even it is identified 250 minerals, but only 250 rare earth minerals. So 3 are economically viable. So that is a bastnanite and monazite and xenotime. As we know, the India, we have the quite amount of beads and minerals where the good amount of monazite is present. So you can see from the seashore from Kerala, Tamil Nadu, and Orissa is the vast the beads and minerals are readily available. It is mined by Indian Rare Earth Limited, and they are beneficiating these individual rare earth minerals from the titanium, illuminite, rutile, zircon, and monazite. So the monazite is now the mineral is basically looks at having the rare earth compounds, which is having the 10 million tons of the reserve base. So if you look into the monazite, actually it is having a thorium and lanthanum based oxides. So once they remove the thorium, this goes for the nuclear application. The rest comes as a mixed oxides. So these mixed oxides are coming as a byproduct from the thorium extraction. If you look the composition of this mixed oxide, it has a cerium is a higher content and neodymium, praseodymium and all. And this was the one of the primary product which is available from the Indian Rare Limited. And this is the base for extracting the individual rare earth oxides. But even we have some expertise, so we can how we can use without separating this rare earth oxide, because we know even though the lot of methods are there how to extract the individual rare earth oxides, even we want to see without mixing extracting these rare earth compounds, how we can use it for the other type of applications. One of the application I just want to share here, the pigments. So this work is we have been working for last 10 years for having these rare earth based pigments. The idea is use this mixed rare earth oxide directly for the pigment applications. So what we found is this pigments, whatever the rare earth based pigment, it has a good chemical and oxidation resistance. So it can be used for high-end pigment applications. So that is the major advantage of this using this mixed rare earth oxides. And even without separating the individual rare earth, so this can be used directly for the freezing. So we have the different process method. So one of the process we adopted for the plasma based process, where we made a pigment grade powder as a very spherical shape powder. So here the idea is using this mixed rare earth oxides for making the different color shades of pigment. So we developed this process and made a different shapes of the pigment materials. So we test the pigment properties and the qualification with the industries, and they also confirm. So this mixed rare earth, which is the primary source of this rare earth oxide, which can be directly used for this type of the pigment applications, even before going for your individual rare earth separation. So that is the one application here I just want to show from the primary raw material, that is the feed material, can be used for the pigment applications. And also we have in CSR NIST, so we are working in various materials development. As I mentioned in the mixed rare earth oxide, where the cerium and lanthanum are quite amount of oxides are present. So we developed the process making this nanoceria by our chemical process method. So which we used for using for various industrial applications. Why this is very important? Because when you look into the primary source from the monazite mineral, and particularly for this mixed rare earth oxide, the cerium and lanthanum are plenty. So today we have a sufficient amount of cerium and lanthanum is present from our primary resources. So we have to identify the different application usage for various applications. So one of the application we developed for this converting this nanoceria, and it is we are testing for the various functional applications, functional coatings for the industrial applications. And I just want to give another glimpse before, as we know, these rare earth oxides, especially this lanthanum, it is also used in pharmaceutical and cosmetic applications. It is well reported, even some of our oral medical treatment as well as the kidney failure, kidney related problem, the lanthanum carbonate use. The idea is in our country, we have a lot of lanthanum oxides. And what we found, the pharmaceutical industries, or they are importing this raw material for their formulation of their tablets and all. But we have the sufficient source of our primary material lanthanum oxides and carbonates are currently available at a very cheaper price. But what we found, there is issues with the residual activity. So what we did, we have with the help of some startup industry, we try to reduce this residual activity level at which is required for the marketable. So we have developed the process, so which we brought this. So this is just having a purification by doing this, reducing the residual activity. So which is this used for the pharmaceutical application. As we can see, we have also the other issues like comes with the trace elemental which is present in this. So we have the process which we developed. So we control removed all these trace elements by our process, which are the values are acceptable range. So this is one of the very important application where your lanthanum oxide as having that residual activity of below I think the required is below 0.2. So even we are trying to work out it. So if it is there, so it can be used for this pharmaceutical and cosmetic application. And as we are NIST, we are the, as I mentioned, this all these trace element analysis, including rare earths, we have the ICP MS facility, which is also we have the enable accreditation. So our values are more viable with the enable accreditation of this. This here I just want to point it out. And one more important area which CSR as NIST is working for last again one more decade. And so this rare earth metallurgy. So as we have mentioned, is already the oxides and the extractions are going on from oxide to metal. So this is one of the important area where you need the product at the end application, whether it is a magnets and other alloys and required for the various applications. So the work we started when you want to melt any rare earth oxide and rare earth metals, so you cannot melt just like in normal crucibles. The first aspect it came in the using this tantalum based crucibles. I remember it even the 10 years before this type of facilities was not there in our country. So in our NIST, so we have developed the process of making the first required the tantalum crucibles, which is required for melting the rare earth oxides to make the rare earth metal. And we have the other process method like calciothermic reduction. And further, the another important is the purifications, because once you extract the final metal may be having some 99.5 purity. So we have the vacuum induction melting furnace, and this is the facility which is the very unique. First time I can say in our country we have the fitted with the condenser with the vacuum arrangement, so that we can collect all any type of materials through the condenser also. So this is a very high temperature vacuum induction melting furnace. Through this melting furnace, so we used to purify the metals, even making to 99.5 to further purification level. That another one is we used to have use this induction melting to make the alloys. So for example, NdFe boron. So this type of alloys also we used to make by using this induction melting furnace. And one of the work which we did it for the refrigeration materials. So as you know, this gadolinium based refrigerant, it was a very important material in that time. So we have developed this process to make the gadolinium metal, as I mentioned. So after this gadolinium metal is extracted in the metal, so we have made the alloy, adding the silicon. So this alloy development, particularly the having this gadolinium silicate and gadolinium silicate germanium, it is a it's not a very easy process. So it has to know the exact alloying condition and thermodynamics. So we have the expertise. So in what condition and what vapor pressure and the temperature we can develop these alloys. As you can see the nice microstructure of this gadolinium silicon germanium alloy. And another important is with this magnetic refrigerant material. So we have the physical property measurement system. So this is the one of the unique facilities available in CSR NIST. You can characterize all type of magnetic materials and properties analysis here. So now I'm coming to the secondary source. So secondary source, as I told this, there is a different sources are there, and also in your previous speaker also has mentioned from red mud and fly ash and ocean bottom sediments also it's available. But I'll talk about the red mud and fly ash and e-waste, what we are working on this type of secondary sources. And also it was already mentioned, the red mud is the one of the important secondary source. As you considered already, CSR in various laboratories having a different expertise, and what we are doing it, I'll just explain to you. So it was also told it is India is producing every year 10 million tons of generation the red mud, and also the alumina producers are also facing a serious problem. As I mentioned, these are the highly alkali content. So for that is the reason this cannot be used in any of the commercial application. But look into the contents presence in the red mud. So iron is the one of the major, and next comes to TiO2, and also there is a quite amount of other rare earths are present, but our focus is on scandium. And as I said, so even if you want to extract only rare earth, so this for particular this type of red mud, the single application is not address a large one, because there is a large volume of red mud is generation. So we have to develop the process as you from the beginning, from the enrichment of remove the iron, whether it is a pig iron as well as the iron based iron enriched rich bearing residue on, and the next comes to the titanium oxide. So what we found in our experiments, the good amount of titanium is present in some of the red mud, especially from Hindalco and other places where almost 8 to 10% TiO2 is present. When we try to enrich the titanium content by our reduction roasting and as well as the smelting process, so we enrich this titanium up to 25%. So this is the very good amount of enrichment where you can remove this titanium, recover the titanium oxide in the form of synthetic rutile. And in this process, already NIST is having a technology how to convert the enrichment of this titanium oxide to the final titanium pigment material. So once we remove, recover this iron and titanium, the residues, as I mentioned, this scandium, which is presence in the 50 to 60 ppm of in the presence in the red mud source. So it can be enriched to 150 ppm also. So, but again, our interest is not up to the scandium oxide. Just I want to give the glimpse, the price of the oxide and metal. Even though scandium oxide has vast applications, can be used in many of supercapacitor and other things, but our interest is the metal, and because the price, you can see the difference. So when you take it to the scandium oxide, it is $4,200, and if you convert as a metal, so it is a 15,000. So this is the value of the presence in the red mud. So we are aiming for this converting in the scandium oxide to scandium metal, and also we have the strong alloy development group. So we are going for the other type of aluminum scandium master alloys, and further this scandium can be used in many other metallurgical applications. So this is our next expertise and the interest on this red mud work. And fly ash, already it was mentioned also our previous speaker, and IMFT already they have got the award based on this alumina and enrichment. Just I want to give the glimpse. So as I mentioned, this rare earths, quite amount of rare earths presence in all these coal-fired power plants, but it is also distributed in many of the in the fly ash in various contents like bottom fly ash and other areas. So we have to identify with different fly ash generation from the plant. So that is the one it is required for the RE, and also it is taken from the reference. So we have the complete rare earth presence in almost these fly ashes, some cerium, lanthanum, and yttrium. But the interesting is some of the rare earths which is very available in very in minor quantities, minor level. So particularly for gadolinium and europium and ytterbium, and as I mentioned, scandium. So these are the very interesting materials. If you can extract from the coal fly ash, so you will have the more value and the economics of the process economics. And as I, this is the normal process flow sheet, how you can extract the rare earths from the coal and coal discard materials, where you can go for leaching and solvent extraction, and finally you can make it by the electrolysis or metallothermic reduction. You can make a mixed or rare earth metals. So where all our CSR labs, we have the different expertise and having this working on this rare earth based extraction. And here I will highlight on the e-waste because electronic waste is one of the also major concern nowadays coming. It is also urban mining of not only rare earths, it is coming as a critical metals and precious metals. So if you look into the electronic waste, so other than this, there is a CRT, LED lamps, LCD, magnets, and batteries. So this all the rare earth elements from starting from lanthanum and yttrium, samarium, so distributed in all these electronic components. So it is also very important source of secondary source of the rare earth extraction. And we had a project with Indo-Australian project. We did some concentration and enrichment of the rare earth elements. So basically we went for the pyrolysis application, it's a pyrolysis process, and where we taken different types of these electronic wastes. As I told, this neodymium, praseodymium, lanthanum, europium are essentially for these electronic components, and these are the presence in the waste PCBs. So what we did it here, so in this investigation, so we have done the concentrated recycling of the pyrolysis process. So we don't burn it, means going at a very high temperature. We have the very selective controlled temperature where you concentrate and enrich the rare earth portions without having the environmental effect. So the dioxin and formations and all we have controlled with our process. So that is the highlight of this process which we developed this to this project. And as also it is mentioned that this demand and neodymium and diosporium, so it is increasing in in various applications in a higher level. So this is the PCBs we were taken with for this experiment, and we done with conventional and as well as the other pyrolysis of plasma. And we have we have done some optimization how to get the enrichment of maximum enrichment of this rare earth oxides. So and even while doing our pyrolysis, so we also get the other products in the separation form. And as you can show that table, this graph. So in different processes, what we found when we have the controlled and selective enrichment of concentration of rare earths. So it's happening like, for example, in lanthanum and gadolinium. So it is the concentration is increased from the 24 to 34 ppm. So now this is the source materials where you can extract the individual rare earth oxides and also metal. And so as you mentioned, this EPCBs means in electronic waste. So this is also one of the potential source for the urban mining for the rare earth extraction. And here I just want to give a little glimpse of this waste. We have a strong group on both alloy development, metallic material. So both in aluminum alloys and magnesium alloys. So one of the very interesting topic, means interest is this magnesium alloys, because this alloy, the magnesium casting and the alloy development. So in NIST, we have the vast experience of making these alloys. And what we found now, the future, whether it is a strategic sector, especially there will be a different new alloys is coming up with the for improving the creep resistance and corrosion and other properties enhancement. So for that also there is a rare earth alloy or metal is important. And what we found is this magnesium neodymium based alloys, which one of the used in very widely in aerospace application, the HAL. So now we are trying to means adopt the process. So to make this magnesium ND, so directly from the waste scrap magnet, because there is a process developed by the Japanese group. But since we have expertise and we have some the different idea, so further how can here actually what they are doing, they are using magnesium as a reductant, and once they reduce it with neodymium, they're vaporizing and taking out. So our idea is to, instead of taking at that, since we can use directly making a master alloys. So that is our approach. And so we have the expertise of particularly this type of making these magnesium based alloys and all. So we were also want to work on this type of making master alloys, rare earth based master alloys, not only magnesium. So we are now also looking for the aluminum based master alloys and aluminum based rare earth alloy development. So already we are framing the work with our group, and we have the expertise and facilities available in CSR NIST. So here I am concluding my talk on what the CSR and NIST has the experience and the expertise on both rare earth materials and minerals, as well as the alloy development and metal extraction in different processes. And so I'd like to give my acknowledgement to our director. So they have been strongly supporting particularly this activity, and also thanks to our director, Madam CSR Sikri, so giving this opportunity for me and also for the NIST to participate this rare earth iConnect program. And I have my former colleague, so is Dr. P.S. Mukherjee. So he was the guiding me in initial all these Indo-Australian project for making these rare earth metals. And our material science and division and all the scientists, even we are each one of us having some activities on the rare earth, that is this lanthanum phosphate or another LED phosphate materials and other rare earth oxides coating. So all the scientists are working in our division, and also I have the students who are working especially this rare earth extraction and e-waste processing, and so also the funding support from CSR, and IRL is constantly supporting all our activities from the beginning we started with the rare earth minerals and materials development, and also the DST last year. So thank you very much. Thank you.
Yeah, thank you, Dr. Jaishankar, for giving us a very elaborative view of all the activities going on related to rare earth at NIST, starting from paints, pigments, functional coatings, and your attempts to produce rare earth metals and alloys by vacuum induction, and your value addition to the fly ash and the red mud activities. Thank you, sir. Thanks for your time.
Thank you.
Yeah, sir, you can withdraw the slides, and may I request Dr. Ram Babu to upload his slides, please. Yes, sir. Yeah. Sir, you can upload the slide, sir, please. Sir, your slides are visible.
Sir, okay, sir, I am audible, sir.
Yes, sir. Yes, sir. You can adjust your camera. Yes, sir. Yeah, it's perfect, sir. Perfect. Yes, sir. Okay. Please,
Okay.
sir.
Sorry,
No problem.
sir. Yes, I got some network issue.
No.
So first of all, I would like to thank. So first of all, I would like to thank our director, sir, Dr. R. Ratish, for giving this opportunity, and also thanks to the directors of NGRI and SICRI for giving this opportunity. So today I am going to talk about our ongoing projects called recovery of rare earth oxides from spent permanent magnets. So I am Dr. U. Ramu, working as a scientist at CMET Hyderabad, which comes under Ministry of Electronics and IT, Government of India. So we are carrying out this project work under the project called Establishment of Center of Excellence on E-Waste Management. So in India, this is the first Center of Excellence on E-Waste Management. So it is funded by MIT, Ministry of Electronics and IT. 40% funding we are getting from MIT, and 40% funding we are getting from Government of Telangana, and 20% we are getting from industry, so industry partners. So these are the goals of this project. So we are going to give the complete recycling solutions for spent PCBs, lithium-ion batteries, and rare earths from different e-waste sources. So the total project outlay is 35.80 crores, and duration is 5 years. So under this project, so we are going to recover from recovery of valuable metals from precious metals from printed circuit boards like gold, silver, platinum, and all. And we are going to recover rare earths from spent permanent magnets, and selective material recovery from lithium-ion batteries, and recovery of valuable metals from waste solar cell panels. So these are the main projects we have taken under this project. So coming to this introduction of this race, Kali Sanjay sir has given a more introduction about this. So there are coming to this rare earths. So these rare earths are two types. They are called light rare earth elements and heavy rare earth elements. So from lanthanum to gadolinium, they are called light rare earth elements, and from terbium to lutetium, they are called heavy rare earth elements. So these heavy rare earth elements are very less common in the nature. So they are very valuable, and also they are very expensive. So most of these heavy rare earth elements are having applications in optical fiber communications and all. So coming to this, whatever rare earths we are extracting from spent permanent magnets are like neodymium, PR, and also in HREE, that is dysprosium is there.
Sir, you have.
Yeah. So okay. So everybody knows that so far China is playing a monopoly in the export of these rare earths to different countries. So earlier we used to depend mostly on China for the import of these rare earths. That's why, so your country has started recovery of these rare earths from its e-waste products. So it is also called urban mining. So this slide shows the predicted growth of rare earth elements demand from 2010 to 2035. So it is gradually it is increasing. So for different applications like ceramics, phosphors, metal alloys and magnets and all. So this is the predicted recycling potentials of neodymium oxide from end of life permanent magnets for three sectors, majorly computer hard disk drives, wind turbines and automobile industries. So it is also, the trend is showing that every year once in 5 years it is go on increasing. The trend is very good for rare earths. And coming to this Niti Aayog reports, so this yttrium, neodymium, dysprosium, europium, terbium, so they considered it these elements as critical elements for 0 to 5 years, and also um, for long term applications for 5 to 15 years also these rare earth elements are considered as critical elements. So mostly we look for this type of rare earth elements in future. So this is the here we can see application wise and this rare earth elements wise. So where we are using these rare earths mainly, like 21% of these rare earths are for magnetic, like lanthanum, cerium, neodymium, terbium, dysprosium, and 7% of these rare earths are used for pass part making, like solid state luminescence, nowadays LEDs and all. So depending upon the application wise consumption, so for regular electronic devices like traditional markets like disk drives, personal electronic devices, power tools and all, we are using this rare earths in grams levels only. Coming to these hybrid and electric vehicles, so for manufacturing of these motors and all, we are using rare earths in kilogram level. Coming to this wind turbine power generation, so we are using this rare earths in a very huge quantity, that is in metric tons. So even in automobile industry also, so if you see each and every part, everywhere we are using rare earths. So these I have taken from the Rare Earth Digest of a monthly magazine. So what they are telling is from 2017 onwards, this neodymium price they enormously increased up to 81%. So neodymium is playing a major role. So recently we have completed one project. It is funded by DST. So what we did here is we have taken this phosphor, waste phosphor from fluorescent lamps and compact fluorescent lamps, and we extracted the rare earths which are available in that waste phosphor. So actually these are the three phosphors used in this production of phosphors. They are like red phosphor, green phosphor and blue phosphor. So if we mix 80% of red and 10% of this green and blue, so we are going to get white color as a complementary color. So this is the composition of the phosphor we are using. So we try to extract this rare earths from this phosphor. So this is the flow chart. So here we are taking this waste fluorescent lamps. So initially what we are doing is, so we are cleaning with water to remove the dust. So after that we are using the bulb crusher. So this bulb crusher is taking care of mercury. So we are not going to leave mercury into environment. So there are some HEPA filters inside this bulb heater. So whatever mercury is there, so it is going and trapped in that HEPA filters. So from by using alkaline water wash, so and filtration and drying, so we are getting this type of white color waste phosphor. This is luminescent materials, and we developed the acid leaching process using sulfuric acid. So here we are getting after reacting with oxalic acid, this rare earth oxalates are we are getting this powder. And in the residue we are getting barium, calcium, magnesium, aluminum and all, lead and all. And so after calcination, we have got rare earth oxides. So we scaled up from 500 grams to 1 kg batch level and all. So we extracted some kgs of few kgs of this mixed rare earth oxides. So every time, so whenever we do optimize the acid leaching process, so since we cannot inject every time using ICP-OS, so since we have this EDXRF, so we optimized, we calibrated the methods for yttrium analysis using EDXRF. So we don't require any sample preparation. So whatever solution we are getting from acid leaching, directly we can use this solution for elemental analysis of yttrium. So this is the calibration curve. So we optimized, we used different normalities of sulfuric acid and came to know that 6 normal sulfuric acid is good for the leaching of all the rare earths. After that, we did solvent extraction using EDTA. So here DEFA we have taken as extractant and we optimized the stripping stages and solvent extraction stages, pH values and all. So this is the summary of ICP-OS results of the rare earths. So actually whatever phosphor we got from this fluorescent lamps, it is having 7% of yttrium, 0.52% of this terbium and 0.49% of europium. So in acid leaching process, it is concentrated to 26%. And finally, after solvent extraction, so we went up to yttrium purity 95.75% and it is having terbium 0.08 and europium 2.48%. So actually yttrium, the cost of yttrium is very, very cheap. And if you see the other rare earths like europium, terbium, actually these europium, terbium, they are used as a dopant, so that normally the concentration is very less compared to yttrium. So we found that this is not a cost effective process because whatever the solvents we use and after production stage, so it is not cost effective. But even to take care the mercury and to avoid the contamination of our land filling and even nowadays we can see whatever fish is available in the market is contaminated with mercury. Mercury is very carcinogenic, so which causes cancer, and most of the fish available in India is contaminated with mercury. So to take care mercury, we have to develop this process. So this is a recommended process. So coming to the topic of extraction of rare earths from permanent magnets. So actually we started our project with by taking the spent permanent magnets of hard disk drives. So majorly it is having Nd, Pr and dysprosium. If you see, there are two types of processes. One is hydrometallurgical process, another one is pyrometallurgical process. So these are the process available in the literature, like recovery of these rare earths by chlorination route, and another one is vacuum induction melting and magnetic separation. So but the purity, if you see, and in this pyrolysis project we cannot easily scaled up like in hydrometallurgical process. So that's why we have adopted a hydrometallurgical process. So this is the methodology we adopted. So initially we are taking this demagnetized permanent magnets. After that we are going for crushing, and actually this while crushing, since the nickel protecting layer is very soft in nature, so it is not crushing, it is just pressing. So while milling, it will be trapped in the sieve. So whatever powder we are getting, it is more than 100 microns. So whatever powder that we are getting, that we are using for acid leaching process. After that, we optimize the solvent extraction, and finally we are going for calcination. So, so we optimize these scaled up the process up to 5 kg per batch. This is the steps involved in extraction, like whatever neodymium sulfate we are getting in acid leaching process, we are taking that as a starting material and dissolving in nitric acid, and we have optimized the pH conditions, aqueous to organic ratio, and number of stages, and optimization of number of stripping stages and all. So if you see the solvent extraction experiments, we can say that these elements are having affinity towards organic phase. So they are Nd, dysprosium, europium, lanthanum, aluminum, and Pr. They are going with organic phase, and sulfur, nickel, copper, boron, cobalt, they stayed in aqueous phase only. So like that, we are going to separate these rare earths. And also we tried, we optimized some conditions to remove this nickel protecting layer using sulfuric acid and hydrogen peroxide. You can see clearly how this nickel protecting layer is removed. After nickel protecting layer, we can see these magnets. After that, we are going for this crushing and all. So this is the roll crusher, as I told. So this is the process for removal of this nickel protecting layer by mechanical route. So this is acid leaching process. So here what is happening, no, depending upon the solubility of rare earths compared to boron and nickel, we are able to separate this neodymium PR dysprosium from iron liquor. So here we are getting rare earth sulfate, and when we dissolve this in nitric acid and react with oxalic acids, it will be converted into neodymium oxalate. So this is the funda we used for separation of rare earths. So here we can see after 50 degrees, these rare earths are not dissolving in acid media. So they will be in precipitated form. So here you can see the spent magnets in each process, how this concentration of neodymium is increasing. So these are some of the peaks of EDXRF of raw magnets, neodymium sulfate, neodymium oxalate, and Nd2O3. So in each and every stage, we have taken EDXRF spectrum. So here you can see the solvent extraction results of this PC880A. So actually in 8 to 9 stages, we are easily able to separate these rare earths. So we tried with DEFA also. We tried solvent extraction with DEFA and PC880A, and we are able to say PC88 is best solvent for separation of these rare earths. And DEFA also we can separate, but that is not that much sharp. So if you see the viscosity of this DEFA compared to PC880A, it is more viscous, and sharp separation is not taking place in each stage. So that was the observation we studied during this solvent extraction experiments. So this is the pictorial diagram of how these elements are separated in solvent extraction. So this is the IC2OS results of spent magnets after leaching. So actually spent magnet is having 30% of Nd. So in acid leaching process, it is concentrated to 62%. And when we converted this into oxalate, so 98.24% Nd was there. So if you this is the process flow sheet. We can see the pictures of rare earth sulfate, iron sulfate, and finally this is the rare earth oxalate. If you want oxalate, we can make oxalate, or if you go for heat it at high temperature more than 900 degrees, will be easily converted to Nd2O3. So actually we found the another way to remove this nickel protecting layer also. So why we did it, actually we came to know that whatever this nickel protecting layer they are using, it is not only nickel, it is also having iron, Nd, and the nickel content is more in this. So there if you remove this nickel protecting layer, there also we are losing some amount of rare earths. That's why, so we developed this process. It is called stripping process. So we got strip A, strip B chemicals from nickel stripping companies. So this is the strip solution. So when we dip this permanent magnets in this strip solution and heated to certain temperature, so only nickel, selectively nickel is leaching. So this is the nickel stripped solution. So when we we studied the pH, optimize the pH condition. So at certain pH condition, only nickel is able to separate. That is converted into nickel oxalate. So like this also we can extract nickel from this protecting layer. So we scaled up this acid leaching process. So if you take 5 kg of this spent permanent magnets, so we are going to get this neodymium sulfate at the bottom. So by filtration washing, so we are going to get 1.76 kg of neodymium sulfate. So it looks like a sand here. So we optimized we scaled up the process. So actually we compared our results, whatever neodymium oxide we prepared in our lab, and this is the alpha acer neodymium ND2O3 procured from the market, alpha acer. So you can see we can compare this two IC2S results. So it is having ND 84% because we extracted from magnets. So that's why PR is also 13.22% PR is there. So whatever neodymium oxide we got, so we can confidently say that this is magnetic grade. So means if you add this ND and PR, it is coming 99.9%. So as such, we can use this for making magnets. So we did experiments and extracted rare earths from laptop permanent magnets also. So these are the laptop permanent magnets. So we got similar results. So only the thing is that these magnets are very thin in size compared to our permanent magnets. So these are the recovered product from our process like neodymium sulfate, neodymium oxalate, neodymium oxide, and we extracted nickel oxalate and iron oxide also. So whatever neodymium oxide we got, that can be used for making permanent magnets again. And whatever this dysprosium you are able to separate can also be used in fiber optical communications and all. Nickel, whatever nickel oxalate we recovered can be used for nickel cadmium batteries, and this whatever iron oxide we are getting as a byproduct can be used as a pigment in paint industry. So coming to the concluding remarks, so we developed a simple and cost-effective process for the recovery of rare earth oxides, and the major impurities iron is removed from 60% to 100 ppb, and whatever this rare earths NdPr, so we recovered is 99.9% pure, and boron is also removed from 1.4% to 30 ppm. And so far we scaled up the process up to 5 kg per batch, and completely. So we checked the effluents and spent liquor also. So nothing is going ND in that. So we can say confidently 99% of ND is recovered in this process, and a patent is filed for this process called a simple and commercially viable process for the recovery of neodymium concentrates from spent hard disk drive permanent magnets. Thank you. Thank you very much, sir.
Yeah, so thank you very much for giving a very exhaustive recovery flowchart for your activities, especially your Center of Excellence in e-waste management and cement hydropack, and your entire activity on recovery of rare earth value from magnets and phosphorus, and which you are already doing at like a multi-kg scale. And we also wish all the best for you, sir, for all your endeavors. So thank you very much, sir. Maybe you can withdraw the slides. So we are already like, although we didn't have one speaker, We had a very exhaustive presentation already. So another two speakers are remaining, myself and Dr. Shivendra from NML. So we will try to wind up as soon as possible and we can go for the panel discussion, sir. So maybe I will just start my presentation. Sir, is my slide visible? Can somebody please confirm?
Yes, it is visible.
Yes, sir. Okay, yeah. Uh, yeah. Sir, thank you very much for having us here. And myself, I'm Dr. Jaykumar. I'm working in CSR Security for the last 6 years. And before that, I had my PhD from IGKR Kalpagam on extraction of platinum from nuclear waste. And after a brief stint at academy, and I'm back to CSR laboratory. So, what is that we are this presentation we will be giving you is it will give you a perspective of all the R&D activities on production of rare earth metals, alloys, and compounds at CSR Security. To no need to tell already, all the speakers have covered this point. It won't be wrong if we call rare earths as vitamins of today's technology, especially whether it is consumer durables or whether it is going to be high-end electronics or the defense applications. Wherever we have a high-tech new age equipment that is having a component of rare earth and that is having a very important critical role in providing that functional property. Now, it won't be easy for us to have the entire value chain of the extractive metallurgy of rare earth, which Professor Kali Sanjay and Dr. Jaishankar have already covered in detail. So we all know rare earth is available in different forms, depending upon what is the ore, what is the geography. You can have more than 15 different minerals available for rare earth. So the typical flowchart is given here, starting from size reduction to the extraction, and in most cases that is leading to an ore, which is in the final product, which is going to be in the oxide form, or either as a pure metallic oxide, or it may be mixture of rare earth oxide. In case of rare earth production, the Indian scenario, as we all know, we have two kinds of ores, which is bastnasite and monazite. One is a fluorocarbonate, and one is a phosphate-based ore. And as we all know, since the Indian rare earth, which is under the DAE, and exploration of rare earth by Atomic Minerals Directorate, they have the full control because we find all these rare earths in mixture with in the monazite ore along with other beach minerals like ilmenite, rutile, zircon in the coastal sections for starting from Kerala up to Odisha. And also we have good amount of uranium and thorium mixed in these resources. So as a result of it, these are considered atomic minerals. And as per 1962 Atomic Minerals Act, so these come Atomic Energy Act. These come as prescribed materials. And as we all know that India has more than 30% of the beach sand minerals which are rich in light rare earths. So it is very critical. We provide a very good amount of value chain for the entire rare earth in the Indian ecosystem. Considering that IREL is producing it in primarily in oxide form, and how is it we can convert it into a useful form? So if you take whether the primary resources or the secondary resources, you have two options. One is you can have a rare earth which is coming from like in the case of beach sand minerals, you can process it, do the different metallurgical hydrometallurgical process, you will get finally the leachates. Otherwise, in the case of secondary resources, you may have additional steps like removal of unwanted scrap, plastics, or some other packing materials, and you go for leaching. And if you are able to go for a salonification and subsequent leaching, which is already covered exhaustively by the earlier speakers, so finally, what you get is a rare earth salt. Either you can convert this rare earth salt into a rare earth metal oxide, wherein you will be having a kind of pure metal or maybe a mixture of rare earth oxides. The other ways you can directly use these rare earth salts for the applications wherein like in the case of where you need a compound or a metal or an alloy, by using a suitable strategy, electrometallurgical strategy like molten salt electrowinning, it is possible to convert them into value added products where you will get a pure metal or an alloy, which can be used for the next generation of application if the feed is coming from the secondary waste. Now you have different kind of routes to prepare a rare earth metal, especially alloys. Some of them are listed here, and the list is not exhaustive. But if you go for directly the industrial application, there are two techniques which primarily compete. One is the reduction diffusion technique or the metallothermic reduction, wherein we use a highly oxidizing material like the calcium, magnesium. We undergo the metallothermic reduction to produce a rare earth metals or alloys. The other competing reaction is the electrolytic process, which is the interest of CSR security, which is a molten salt electrowinning technology, wherein you can use other oxide as or halide as a feed, wherein you can produce rare earth metals and alloys. So before we go to the molten salt technology, the simplest to understand what is a molten salt is nothing but you take a salt and if you put in a solvent like water, what you get is a solution. It's a typical textbook case. Now, if you take a salt and if you go to very high temperature where it melts, that becomes a molten salt. It has very high conductivity, which is at least 10 to 100 times higher than a normal electrolyte. And also, you can do the electron winning of any metal which is there in the periodic table in the metallic form. So, which means you theoretically you can deposit any metal using molten salt field. So, what is it we are trying to do with respect to CSIR is if you take the case of extraction of rare earths, you have multiple options. Say you can have the primary source or the secondary source, since they are along with the beach and minerals in monazite that comes under the purview of IREN, and also the exploration in the inland carbonate, fluorocarbonate also comes under AMD. So there also CSR NGR is having a critical role there in mapping and utilization of this whatever geographies where this non-aerial based minerals are being explored. And in the case of secondary resources, the CSR laboratories like our IMMT, NML have a very critical role. And actually, as presented by Dr. Rambabu, CMT is also having a role wherein they have already a process to extract these rare earths either from primary sources. You also get it from them from the secondary waste like our lifestyle products such as spent magnets, phosphorus, etc., and industrial waste such as red mud and fly ash. So all this comes to one place where either it is converted into oxide or carbonate. So in the case we may need to go for to convert them into a suitable product, because oxide is not the desired product for all applications. Where like in the case of glass industry and specifically like catalyst industry, some places they use a good amount of oxides, pigments especially, as Dr. Jaishankar has told. But there are places where we need a pure metal or an alloy. That is where CSIR is having its own indigenous technology, wherein we go for rare earth extraction by molten salt technique. We have a very strong experience in this field, and we using rare earth oxide or rare earth chloride or fluoride as a feed. We have developed different protocols wherein we can get a pure rare earth metal with in excess of 99% purity. We have a scale around 100 gram, and we are now going for higher scale. And the another protocol is we can develop rare earth based magnetic materials such as alloys like samarium, cobalt, and NDFE, which we can do at 250 gram per batch scale. When I say one batch, it is around 6 hours of electrons duration. So if you go for 3 shifts per day, you can go up to 750 grams or higher. So that is the scale we have at CSR Sikri now. And we also have protocols to develop rare based compounds, such as in this case it's boron, because they have very specific applications. So we are doing a different rare earth borate extraction by molten salt techniques. So we all know that rare earth based magnets primarily, whether it is in defense or in the commercial usage, you have two applications. So you have either samarium cobalt playing a vital role, especially at higher temperature application, but it is costly. In the case of NDFEB, that is for most of the miniaturized and the windmills, for the clean energy applications and all for the electric vehicle applications, it is having and the defense applications, NDFEB is one of the most sought after magnets. So what we are trying to do like in our CSR system, especially CSR series, whether it is a primary magnet or the secondary magnet, because as we all know, as Dr. Kalishanji has already mentioned perfectly, that if you take a wind turbine, you have more than 50 kg per megawatt of rare earth content for every megawatt. And if you take a car, you can have like if it is NDFEB and dysprosium, you are going to have close to 2 kg of rare earth. So whether it is going to be the defense technologies, so are the IRL based primary resources, primarily since that is fully extracted by IRL in oxide form. So at CSR Zuburi, we are trying to develop the protocols for both rare earth metal and alloys. We already have, and we are now going for scale up, wherein we are also trying to see whether we can do value addition and convert them to the actual magnets also. That is our plan in future. And to add some of these points, we can see there's some overlap between our CSR laboratories also. So what we have done at CSR series, we also have ongoing programs and development of rare-based light metal alloys whose applications have been already discussed. So wherein your low-cost, highly available materials such as cerium, lanthanum can be utilized for these applications for specialty light metal alloys, especially for automobile applications and defense applications. And as I've told you, these borides, which have multiple applications, like in the case of neutron absorbent or electron emission, wherein you can use this kind of borides for very specific applications. We have a protocol wherein we CSR Sigri can develop rare earth borides at different scales, depending on what is the rare earth boride we are looking for. And this we know that hydrogen storage materials also we have some more activity wherein this AB5 type of alloys using low cost rare earth and transition metal alloys that can be used for hydrogen storage, and that's also an interest which at CSR Zikr is working now. So to conclude, whatever we have we are doing at CSR series, we have capabilities to develop molten salt aluminium of rare earth metals and alloys at different scales. Primarily, the metals which it is lanthanum, cerium, and neon at 100 gram per day. And in the case of alloys, it is NDFE and lanthanum nickel at 250 gram per day. And we also have protocols for developing light metal alloys like aluminum based alloys at 500 gram per day. And if we are taking the coating metals, like especially in the case of lanthanum phosphate, we already have a technology and we are going ahead with the IP filing, wherein we can produce 500 gram of these high temperature coating materials like lanthanum phosphate and initiate multiferous materials like rare earth borides at the CSR degree at different scales like 500 gram and 50 gram per day. So what we are trying to do at the CSR degree is to provide a overall value addition to the entire Indian rare earth availability. Like in the case of whatever IRL is producing in oxide form, which we convert into a suitable iron oxide or into the chloride form, which we are trying to convert into a metal alloy and compound at CSR60, which can be maybe technology transferred to a suitable agency and which will be able to provide, as Dr. Kalishanji has clearly pointed out and also told by Dr. Jaishankar, that the entire value chain for the rare earth based systems, especially in the case of metals and alloys, CSR is trying to present itself, and we are going for higher scale up of whatever existing process also. And we are also open for collaborations and discussion with other industrial partners and other labs such as CMET also. Thank you very much for the opportunity, and thank you. Hello, Dr. Shivendra. Hello. Shivendra?
Dr. Jaykumar, am I audible?
Yeah, Shivendra. Yeah, I think you can please upload your slides. Mr. Shivendra Singh is working as a scientist in CSR Enamel, and he has more than 7 years experience with a metallurgical background, and he has worked on various extractive metallurgy schemes, especially for value addition in terms of zinc, manganese, tungsten, etc. And also he has more than 3 technology transfers, and he's one of the dynamic scientists at NML, and I look forward to your presentation. Shivendra, you can upload your slides, please. Shivendra,
Dr. Jayakumar, are these slides visible?
no, not yet. Not yet. I was mentioning it is starting, but no, it is not yet visible. Can you please share it again? Yeah, now
It
it
is
is
visible.
Yeah, it is visible. It is visible. Yeah, okay.
Oh, okay.
Yeah, okay. Please.
So this work is on the their separation from the waste or dilute solution, what we are carrying out at CSI and NML. Talking about the critical raw materials, it is already evident from the past presentation that these rare elements are very critical in nature with regards to its wide usage in technological development and materials. Considering its realization of the material with regards to the supply research versus the economic importance, we may see that with a graph of supply risk and economic, these metals are at a very high supply against their wide usage, which are exponentially growing in the coming years in batteries, catalysts, and several other applications. Now, coming to its importance, these metals are very critical to its wide usage and critical technology usage, and therefore there is a need to look at increasing production through secondary sources against the depleting and scarce primary resources, and where the wastewater effluent or dilute leach solutions are potential secondary source for metal recovery. Coming to the methods of separation of layers from such solutions, either dilute effluents, leach solution, wastewater, we have a couple of techniques: chemical precipitation, flotation, ion flotation, basically membrane filtration, solvent extraction. Some of the speakers have already discussed. But when we scale down the concentration of these metals in the ppm range, so adsorption in that category, adsorption based technologies are widely used with a low cost of application, easily handling, and with a purpose to pre-concentrate these metals in a small quantity to a much more concentrated solution, or to separate these metals from other metals, from the effluents from the tailing area, or from the effluent generated during the hydrometallurgical processing of primary and secondary resources. Now, any inorganic material cannot be used for separating the rare earth metals out of the solution. We need to have the tailored binding group present over the surface of such material, and that is why we need a functionalized base material for the separation of rare earth, and these are the critical parameters responsible for the adsorbent performance, where recyclability selectivity and scalability are the crucial. And generally, the mechanism involves the service complexation, ion exchange, electronic or electrostatic interaction. Now, the main point is that we have worked in the area of development of these adsorbents, like silica-based adsorbent, graphene oxide, and ADTA, where basically all these functional groups are responsible for chelating this metal ion from the solution. Now, what decides the success of such kind of adsorption technology? The choice actually relies on the adsorbent characteristics, where all these parameters are very important. But I would like to highlight the scalability in terms of uh, 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 the ability of the adsorbent material to be used in the column mode. So far, so now, more than 95% of the adsorbent developed are the powdered material, which may have good characteristics and may not have a good characteristics. But again, these are the powder material, and they have no practical utility whatsoever at the practical on the ground scale. Besides, they have their excellent characteristics in terms of the selectivity of such material for errors than the other metals like transition metals or alkaline metals at the very high sort concentration. Now, coming to if we have the adsorbent with a good characteristics but with poor scalability, can we use such powders with a good characteristics in column? So we have developed a composite with polymer to form of such material with the in the form of spherical polymer beads. And similarly, with the poor characteristics adsorbent, we have for the development of a new adsorbent with excellent characteristics and good scalability by blending it with a polymer. So let's take the case one that we have worked out, the graphene oxide. Why we chose that graphene oxide? Because why we have chosen this thing? Because it has excellent adsorbent characteristics derived from the carbon, therefore it has a high chemical stability, and it can go for the recyclability up to 20 cycles with a 98% efficiency. Now, what's the issue is that you cannot use a powder material in a column because you have a difficulty in the solid liquid separation, and there is a loss of permeability in terms of excessive energy requirement against the pressure drop by using such kind of powder material. So such graphene oxide has an adsorption capacity of 480 milligram per gram and has a selectivity over a KD value of more than 7,000. Now, how we fabricated? We fabricated a very low cost polymer based phase inversion technique where we have developed the kind of GO, that means graphene oxide incorporated pan beads, which has an adsorption capacity of 120 milligram per gram. And we have done the column runs using a simulated effluent generated with the in-house processing of NdFeB magnets, where after the precipitation of the neodymium, you have still some amount of endymium left in the solution, and you try to recover it such process. The other case is attractive use of metal organic framework. These kind of material has a very high surface. It may go up to the 10,000 meters per gram. And the best part of such material is that it can host variety of ligands which are responsible to take the metals out of the solution. But some of the materials also has inherent functional groups. So not all kind of MOFs can be used for the separation. They have to satisfy these criteria and can be used for the separation of such metals from the solution. And MOFs are very relatively less explored in the separation of it, but has superior potential for such applications. one such applications that we explored for the separation among the rare earths. It's very with regards to rare earths, we have a very scarce material which are effective in the separation of rare among the rare earth elements. So in such cases, we have explored that the separation factor has a value of 6.4 for the combination of these metals. It may go up to 31 times. But the main point I would like to highlight in the existing set of solvent extraction technique, we may go up to the separation factor of 3 or up to 2.6 with the relevant defined PC88A in certain studies. But on such materials, so we can go up to the separation factor of 30 to 32. So therefore, it has a very high potential in terms of the separation of these metals, but it is limited to the metal concentration in the ppm range. We have prepared such kind of composite of such kind of MOF, and it shows a capacity of 1050 milligram per gram, which is one of the highest reported adsorption capacity for the rare earths. We have also prepared this kind of composite for the separation. The best part of such composite, they can directly be used in such kind of columns, and we have done the column with the effluent generated from the processing of the waste containing samarium and lanthanum. So basically, such kind of materials can not only be used for the separation of rare earth from other metals, but can also be used for the separation of the among their own fellow elements. Now, what's the future of the adsorption technology? Almost every hydrometallurgical process from primary and secondary RE resources and its related mine area release such metals in leach liquor, effluent, wastewater, along with other metals. And adsorption-based technologies are the most facile methods to recover these REs from such solution. And there's been increasing emphasis on the recovery of secondary sources may further widen up the acceptance of such technologies. Challenges like the high separation factor, scalability, and recyclability are critical in such advancement for wider and industrial acceptance. And the future way ahead is the use of such low-cost methods for synthesis of such adsorbent, which may further help to realize the commercial viability of such technologies. We have Chalex 500, Chalex 100 kind of commercially available adsorbents available for the separation of rare earth out of the solution, but they cannot separate amongst them, and they are just able to separate all the rare earths selectively over transition elements. And taking that as a benchmark, the developed material has a much higher adsorption capacity, almost 1.5 to 1.7 times in case of graphene oxide, and in case of pan MOF based composite, it may go up to 15 to 18 times. So yeah, thank you. Apart from that, we also have a portfolio of RE recycling from end of life magnets, and we have already upscaled, and we have a TRL level of 6. We are coordinating with a company based out of Pune for the further process development and its transfer. And the products are mixed rare oxide, sulfates, and chloride, etc. We have also ongoing development in case of fused solid electrolysis for the recovery of neodymium from the salts. If you have any other queries, you may please write to me on this number. Thank you.
Shivendra, thank you very much for your presentation. So you covered because all of the presentation was extraction of rare earths from highly concentrated solutions. You discussed in detail regarding solid adsorbents and their role in extracting rare earths from tailing and dilute solutions. Thanks for your presentation. I thank all the speakers for giving excellent presentation. Now, actually, although we are behind the schedule, but we have come to the most critical part, which is the panel discussion. And before I start the session, I also thank the patience of Dr. Vikram Dood from Ashwini Magnets and Dr. Ratish from CMET. Now we can start the panel discussion. Maybe, so can you all? We can all switch on our video also. Yes, sir, it's going to be my request. Yeah, yes, sir. Okay. Yes, sir. Yeah. Sir, actually, the main aim of this industrial iConnect meeting was to bring the entire rare earth family, whether inside the CSR, whether it is the industries, and maybe we try to get in IRL also due to some last minute issues. He was unable to join. So we would like to, from the organizing side, maybe we can just get some initial remarks from Mr. Vikram and Dr. Ratish. Then maybe we will just kickstart the panel discussion. Maybe the floor is open to you, sir. Maybe you can just give some initial remarks.
Thank you, Dr. Jaikumar.
Yeah, thanks.
It is a very nice experience to have all these fantastic speakers going through these technical papers. I am feeling very excited about all these technologies that you have put on screen today regarding recycling of the spent magnets and others also. Look forward to discussing this with you in further depths in the times to come.
Yes, sir. Okay, thanks.
Dr. Jayakumar. At the outset, I thank Director Sikri and yourself for inviting me for this panel discussion. As you know, CMET is promoting resource efficiency and circular economy in the country, not only on the recovery of rare earth oxides, but we are also into all other kind of e-waste recycling. So we promote urban mining, like we have a PCB recycling technology up to 1 ton per day, which is ready for transfer to interested industries. We are also into lithium-ion battery, end-of-life lithium-ion battery recycling. See, you know, as the name implies, I connect, like, you know, this, I feel that this is an intellectual connect, wherein, like, you know, we are all working at isolated pockets. There is a need to work coherently, like, you know, then only we can ameliorate these technologies and so that it will be benefited for the nation, like, you know. So with this, do you know that there are examples in other countries, Europe, there is a sustainable magnetic program, which is called the SUSMAG Pro, sorry, Sustainable Magnetic Production, where the entire Europe is going to recover the rare earth oxide only from end-of-life permanent magnet. Okay, so we will discuss in later, like, you know, how to go about, what are the criticalities which we need to look at the Indian scenario. And thank you so much. Thank you for all the, you know, expert who has given scintillating lectures today. Thank you.
Thanks. Thank you. May I invite Dr. Kali Sanjay to give some initial remarks, sir?
I agree with CMET. Basically, we are all working in pockets, and I can see a lot of replications, and then there are a lot of areas where we have competence all over the country. And it's time that we should gather all our know-how and then facilities also, because some people may be having a process and other places we have the facilities. If we share, and we can fastly develop these technologies, can go for a commercialization at the least. I look forward for the discussions. Thank you.
Yes, sir. Thank you, sir. Yeah. So actually, just there are some few points. I think I will just give lead. Maybe I think we can all discuss in those points. Like there is nothing like somebody can always put in their points also. So how is the present ecosystem for rare earth, especially from the industrial side, and how is it when you have a geopolitical situation like from China or US, then there's an issue. Then how it is getting impacted with the rare supply and cost? That is one thing we would like to hear from the industry. Maybe Mr. Vikram can just to give us a feel. Then how is your interaction with the Indian R&D institutes. Maybe you can. What is the expectation from us? Because we are on one side, we are working as Dr. Ratish and Dr. Kalisan they have mentioned. We are working in isolated pockets on different aspects of rare earth evaluation. And on the other side, IRA is also working on different aspects of rare earth extraction. So, what is the present rare earth ecosystem and how you manage with this geopolitical situations? Maybe you can just give some little input on it because you will be having
Yeah.
a day-to-day experience and you will be handling different other aspects also.
Yeah. So we have been importing basic NdFeB alloys from China for a long time now. We've been using this for manufacturing of injection bonded NdFeB magnets also. The first probably injection bonded NdFeB magnet that we made was way back in 1998. And since then we have been importing NdFeB alloys from China. The prices, everybody knows how they have, how the Chinese state as well as the Chinese manufacturers are hand in hand in extracting the best possible prices from the entire world. You know. So looking at all that a few years back, this fantastic entire drive started where India started working on NdFeB materials, right from IREL, Niti Aayog and everybody. So for us, it was a very welcome move from our side. And we recently, last year, had an MOA with BRC and IREL for production demonstration of PRND metal made from Indian rare earth reserves. So that is, my team is working on that and it will be established very soon. The basic issue remains the techno-commercial viability of this in India. So if we basically talk about the prices on SMM or on the Asian Metal Index, your rare earth oxide price and the rare earth metal price, the difference is so maintained that no manufacturer in the world is going to make any profits out of that process. You know, so looking at it from the industry perspective, it is not lucrative at all, and that's the reason you'll not find many people coming forth to establish such plants. And one basic process in the entire supply chain, that is the metal making process, has always been non-existent in the country. You know, so that's how a lot of research agencies have been involved in getting this established. Of course, there are many routes, right from calciothermic to your MSC, molten salt electrolysis. So going by any of these routes, we have still not been able to establish techno-commercial viability of such projects on a large scale. No, so that is one big aspect that needs to be discussed further. Further to getting a neodymium metal in hand or PRND metal in hand, the other further stages of manufacturing of magnets are also non-existent in the country. They are also at all stages at different places in the country being worked upon. We do have many business cases made at our end where we are putting up a small plant for manufacturing of sintered NdFeB materials also. But there too, economic viability is not there on paper. If I use the ND metal according to the SMM price, and I compare the end product price with the end product that the Chinese people sell, it is nowhere in comparison. Absolutely nowhere. So, you know, these adjustments made by the Chinese manufacturers with the Chinese state and the backdoor subsidy, all this that is happening, that's the reason this industry has never grown anywhere except China. So that needs to now be highlighted at a larger level, and something needs to be done on that front also. Yeah.
So, like, I think you may be already in discussion with maybe like IREL or Niti Aayog in developing such an ecosystem because you are going to be the end user, one of the largest.
Yes, we are in discussion.
Okay, great.
Can I add to this point?
Yeah, please, sir. Please, sir.
Yeah. What Vikramji is telling is the highlighted one of the slide where I was highlighting that there is a gap. So we can get on all oxides, and then there is a downstream process up to once we have the alloy available. And the problem with the magnet manufacturers is availability of high pure and then in an alloy form, right kind of alloy form, what he has rightly addressed. And one of the part where the CSR AMP is going to work, as you mentioned, it's possible that calciothermic process is there, but the cost viability. So what we are planning to do is a straight away with a step of 300 amps, a 3 kilo amps, which is the base Chinese model. Now, Chinese have gone up to 10 kilo amps. Of course, when you go for higher scale, it's known that molten salt electrolysis will have lesser energy requirements and more energy efficiency, and purity is also good. But however, the base model where Chinese have been selling at that cheap cost was fluoride route and 3 kilo amps. So we took that as a base, though REEU has started and then they developed 15, 16 organizations with 1 kilo amp, because that was a step still not commercial level. So we are aiming at straight 3 kilo amps, and that, let's see where we fail at that level, because you go into smaller levels, you don't know the problems which will be ending up at that level of base this one. So CSR AMP is basically working. We are just about to start the project. We are in the consultation for the funding and all. And this is as per the Niti Aayog's directive that we are taking. Just to add to your.
Yeah, if I can add a little more, on the MSc side, we have been in touch with some Chinese vendors also. And now there is absolutely no availability of these 3000 or 3 kilo ampere electrolytic cells. The base model that they have shifted to now and being manufactured in China is 8000, that is 8 kilo amperes, that is available for the industry in China. They moved on from 3000 or 3 kilo amps to 6 kilo amps and then to 8 kilo amps. That's how they have progressed, and a lot of this is being established there in China even today. It is not coming out of China at all. To get it out of China, you have to strip it into parts, small parts, and get it. I mean, that's the way it's being discussed.
Yeah, I know that they are. That's what I mentioned. They are now going for 10. 10 is their base.
Yeah.
And your two advantages still there. One is the purity comes when the larger scale, and second thing is the cost economics is better. But still, the bottom level where China has been working all through these years and middle 2000s and all was not now present, was 3 kilo amps.
Right.
So at least we should reach that level so that we should be able to fastly. If we could jump straightly to 10, I think we'll be ending up into too big system failures. So 3 amperes is a correct level where we can start. That's the reason why Niti Aayog suggested that's the target.
Right.
Sir, just to add whatever that Kali Chandya has told, like at CSR Security, we already have a couple of IRL sponsored programs. So wherein we are also producing like a PND at a different scale, like some of them I mentioned. Now we are also going for scale up. We have got some desired purity, and as you told, two things are there. One is the techno-economics, and another one is something related to the purity level, because you are like expecting upwards of 3.9, right? 3N and higher purity, and you don't want any of the specific some metals like say refractive metals, tungsten or molybdenum should be there. That is very detrimental for your final magnetic property. So that is one more criticality is always there. So like I think Chinese, maybe sir, Vikram, you can just add a little more. So the Chinese is primarily they want to keep their monopoly in the commercial NDFE market, if I'm not wrong, right? So they want to give only the product, not the process, nowhere, whatever may be the cost. Am I right?
Absolutely. So it's been a big, long drawn strategy there where they had realized the potential of these materials way back in 1980s and 1990s. And since then, the strategy has been put in place. I mean, we do remember our discussions and our probably meetings with the Chinese also since the late 1990s, when actually the Americans had started going to China to establish the plants there. So we have a long knowledge of all this, and we've seen them do this for all the time.
And also, if I have to quote, maybe he's not there. CMDF, IREL, DSync, I think he told like the Chinese state has different policies, right? They sell in open market and also in the oxides, they sell it through some third party in a black market. Also, they somehow control the entire rare earth casting in such a way that nobody else can offer.
Absolutely.
And also they also have like a geopolitical strategy to use Africa, then South America, wherein they also have some rare earth exploration in addition to China, so that they can have the supply chain long into the future also.
It's not only for the ND metal technology, even downstream. If we talk about magnet making technology, the first process of strip casting furnaces. If I have to import and strip casting furnace today, I have to wait for 6 months and send an application to the Chinese state, and they only if they approve of it, the strip casting furnace will be shipped out.
Okay.
So there are embargoes.
Yeah, that's what. And also they have a different system altogether. That's totally different from our system. Shivendra, your hands were on. You want to add a point?
I just would like to know a couple of things from Vikram sir of Ashwini Magnets. The first point is that what's the current state of the companies who are into the fabrication of ND-FEV magnets in India? That's the first point. Second, with regards to ND, we are talking on the recycling of the ND-FEV magnet. Kind of the collection system so far developed for identifying such scraps and the collection of such alloys from different end of the life products.
Sir, I lost your second question. Somehow could not hear it properly. I'll answer the first question first. So there are not a lot of ND-FEB manufacturing companies in India. Whoever is manufacturing ND-FEB magnets in the country is cutting it from the blocks that are being imported from China. So there is there is absolutely no production scale or industry scale manufacturing of ND-FEB magnets yet in place.
The second case is that when we talk about the collection of such scraps, so whether there is what are the scraps generated during the fabrication of such kind of magnetic components? Because there must be the end of the life product, and during making there is some scrap generation or solve generation during its production.
Yes.
I think we have already collaborated through one of your partner, I suppose Bhaskar is there on such recycling route.
Right.
Yeah. So I would just like to know the current status of its production on a wider scale. And are there any other companies who are also producing such kind of scraps in India or not? That's what I would like to know.
There are a couple of companies who are cutting the blocks and making magnets out of them. And that's the usual route that is done in China. There is no net shape manufacturing of ND-FEB magnets yet in place. So probably there is more than 20% waste at the cutting operation itself. So there is a lot of scrap generated from blocks when they are cut to final shapes. We do have quite an amount of scrap of ND-FEB scrap at our end also, because we do these cutting operations, cutting, coating, magnetization, and further supplies to in small ways to a lot of companies. But for the ND-FEB sintered magnet processes, they are not yet in place at our end. So we are still working on establishing of the ND-FEB sintered magnet small facility at our end, and that will be established only after we have the ND metal establishment here. We are doing a 3 metric ton per month ND metal establishment first, and post that we'll be having the ND-FEB permanent magnet manufacturing facility. To add to what to your reply there, in stages of manufacturing of permanent magnets, yes, there are going to be at every stage there will be some kind of opportunity for recycling. Yes, after it is converted into a crystalline material by strip casting, there are always going to be areas where there are going to be wastages and can be collected and taken for recycling.
So among the various products that you have seen in the presentations made by all the speakers, like neodymium oxide, neodymium chloride, or other products, uh, with your knowledge, I would like to know the most accepted technology in the market available to extract the ND out of such material, because I want to know two particular things: the widely accepted technology and the most acceptable material to feed to that technology. If you have some idea about that.
Probably I am not the right person to comment on these technologies, but if we are talking of conversion from oxides to metals,
Yes.
yeah, so then I think molten salt is the way.
Fluorides based or chloride based?
I beg your pardon?
If fluoride based or chloride based?
Fluoride based. Fluoride.
Kali.
Yeah. It
Yeah,
has
Kali
to be,
Sanjay sir,
yeah.
I would also like to.
Yeah, the entire
comment.
China is working on fluoride based chemistry itself. So it's fluoride electrowinning only. Neolithic fluoride.
Yeah,
So I would like to request request Jay Shankar sir and Kali sir to just comment on the fluoridization of challenges during the fluoridization of such kind of rare earth oxides. To just highlight in terms of the practical.
I will tell you, there is a Niti Aayog committee which has worked almost 1.5 years or 2 years, and to set up this oxide to metal facilities in the country. So one aspect is that there is technology available from SICRI, which I think calcium metal. So that technology is there. That technology was used and then they have produced some metal, and then that was in turn used by BARC for calciothermic reduction. That's one aspect of that thing has been studied. The second aspect was on chloride, where NML has an experience, and SICRI also had an experience of chloride-based technologies, and so they are still working on the developmental. But what he has already mentioned, Ashwinji, the known commercial process is, as of now, is fluoride molten salt electrolysis. So CSIR-AMP has been assigned this task by Niti Aayog to go for development of 3 kiloampere cell. So it's a chemistry is known, but there are a lot of technological challenges such as ND2O3 dissolution is very low in case of fluoride, and the issues of slag formations, issues of purity, carbonations. So only once you burn your hands at that level, we will come to know. That's the whole purpose why China is putting that restriction. It's not that we cannot do it in a small scale and the chemistry is not known. But when you do it that level, there it is expected that we have a lot more challenges. We will come to know only at that scale. So that is the reason why the CSIR-AMP has been assigned this job. While I think other labs are also being recommended to continue whatever the innovations, like even NOS is there, a new process. So that still people can work. They will be better this one. Second thing is why this also have some backup this one, because in 2015 when RE European Union RE for you, so when they started looking into what technology that they should look into by formation of the group, like 16 organizations including academia, industry joined in hands, they also selected the fluoride. So known commercial route is by fluoride molten salt electrolysis.
Yes, but still there are the challenges with respect to achieving the purity of oxides with respect to the basic raw material.
That's the reason why one good part of it is that you get ND in direct form, while you might require vacuum distillation, further vacuum distillation to get more purity in a calciothermic reduction or chloride process. So what I'm saying is everything has its own challenges, ups and downs, but known commercial by is
Jaykumar, can I add? Yeah.
Yeah, please, sir, please.
So, yeah, just to add on this, the discussions, because mostly it is related, since the industry expert from Magnet, as Vikram sir has told the issues. So as per the process concern, where you were our Enamal Singha also asked that calciothermic reduction is another issue, the source of calcium. So that is also it was the source. It's not, but what I understood now, we have in India, even CSA lab, we have some technology to produce the calcium metal in the economical way. So once that comes as in commercial level production, like other metals coming way, so then that process also can take up in not for the as extraction, but what I mentioned is alloy development, further vacuum distillation and purification. And also as per the NIST concern, this calciothermic reduction, this work also started in for last 10 years before with I showed the gadolinium silicate. But this type of alloy development and where we have the particular phase formation, I still means remember this NDFE also having some particular phase constituents present, should be the ND2FE or some modification of phases. So this process, whatever the calciothermic, it can help you in that aspects, making the particular phase alloy. And this is related to magnetic, but as a rare earth concern of in our country, and what we feel that we have to find a lot of applications, because as mentioned in pharmaceutical, just they importing, even their requirement is also again almost coming in the not 1 kg or 2 kg. They are also looking for some 500 kgs type of rare earth oxides. So, but it is not whatever the source or whatever the products which is it is not directly applicable to that. So they are also importing. So what I want to mention means pressure is here. So as we are in CSCR and as well as the CMET, and we are having process for producing the various rare earth oxides and metals. And now this is the time to find the applications in diverse areas. It is a pharmaceutical and medical, as well as the whatever the strategic sectors where you need the high temperature materials or oxidation. We know this rare earth oxides having the lot of properties from the based on the chemical or as well as the mechanical and other thermal properties. So as per the with the NIST concern and CSR concern, so we all also look into the applications and invite more industries for this type of discussions. And also we are also means looking into, there is another aspect, critical metals also coming in the big picture. And with this similar process that can also be addressed for extracting and usage of various critical metals in our, which is a huge requirement for our country, for country needs. So thank you very much.
Yeah, just to add, Dr. Jaishankar, actually, like in the lot of discussion is going on regarding the fused salt or molten salt electrolysis, and we all know like whether if we need calcium also, we have to again calcium or magnesium. We have to again go for the molten salt process only, wherein we will get a high purity metal that you have to go for distillation. Like I have told, several speakers have told, especially Dr. Kali Sanjay, like Sikri was already having a calcium and magnesium plant. Then there was some like maybe due to policy decision at higher level, or maybe and there were not such very good emphasis that was given to this continuing this molten salt process, especially at CSR Sikri. Like each of the CSR labs, they have their own competencies. Molten salt technology, especially for the production of calcium and magnesium, was one critical part of CSR Sikri. And there was more than 1 or 1.5 decade wherein we lost that niche area, and we are trying to regain that strength. Actually, now we also have a active group which is working on calcium and magnesium electrowinning. Just to add whatever process we have told, because for BRC they want to use this for their strategic application, maybe for uranium or plutonium, and they have a different process altogether using this calcium and magnesium. So that is the state of the art, and that is where exactly Vikram has told, like when for the last 2 decades, especially till 2015, when Trump came for the US as a president, till the time the Chinese have for 2 decades, they have literally taken the monopoly from the rest of the world only to them, and they started supplying left, right, and center with the highest purity, and nobody knows what is really going on there. and at the lowest cost, whatever may be the cost. Once they started getting the monopoly, I think subsequently they started doing the cost control. And last few years, there's a revisit of these technologies, especially when there is a post Fukushima, there's a lot of interest on wind, especially offshore wind
Wind
energy
turbines.
production. And a lot of countries, especially the European Union, Germany has literally closed their nuclear power plants. So many countries are revisiting their own new green energy techniques wherein you can use these rare earth magnets, and they are also revisiting their own rare earth extraction strategies. Maybe I think we are also discussing a lot about the primary feed which is going to the magnets, and maybe I would like to hear some more from Dr. Ratish also. Like if you go for rare earth recycling, because you have a dedicated center of excellence at maybe Dr. Kali Sanjay also can add subsequently. So what is your feed with respect to the recycling? Like if you take maybe you know it better, like in the case of lead acid battery, more than 95 to 98 percentage of lead acid battery is recycling, because that is because the seller itself buys back. There is a proper ecosystem wherein the seller themselves buy back the battery, and that goes for the end of cycle. So there is no amount lost, maybe very few percentage. So what is your opinion with respect to the rare earth phosphorus, or especially the magnets? Maybe you can just show some light there. Yeah, please, sir.
Before answering that question, I want to add whatever Dr. Jaishankar has pointed out now. You see, like we are mostly discussing about permanent magnets. Apart from that, there is a lot of requirement for rare earth oxides. Basically, my area of expertise is on ceramics and composite materials for wireless communication application. You know that countries now all set for going from GPS to NAVIC. Okay, during Kargil war, America did not extend GPS to India. So we have already launched 9 satellites, and we are all set to translate from GPS to NAVIC. The requirement of NAVIC antennas in the country is almost 28 million pieces. Currently, I am developing or already developed dual band and tri-band antennas for NAVIC application, wherein rare earth oxide is one of the very important requirement. That means huge quantity of rare earth oxides are required for producing rare earth based ceramics for NAVIC antenna application. This is one requirement. The next requirement is so we are also into microwave printed circuit boards. This is called the RT-Droid. There is only one company in the world manufactures this. And the cost of this circuit board is almost $250 per square feet. It requires almost 65 to 70% of ceramic filler material, wherein rare earth oxide is one of the very important requirement. So I am also an alumni of CSIR. I was attached to NAST. If you go back and look at the scenario from 1990 to 2000, we are getting rare earth oxide from IRA. Now, if you look at, as today morning Director Sikri has mentioned, we are 5th in the world as far as rare earth reserves are concerned. We have 7 million tons of monazite available right from Kerala basin to Odisha. But the processing of these particular materials are only 5,000 tons, out of which half of that is produced by a Japanese company called Toyotsu Rare Earth Private Limited, which is located at Visakhapatnam. So IRL is channelizing some of these materials to this Japanese company, and they are processing up to foreign purity. It is going to either to Japan or China for further, this permanent magnet manufacturing. So if you look at the Indian scenario, in 1950 itself, we have established IREL. We have visionary leaders like Homi Bhabha. And I was astonished to note that they have met even the Travancore prince or king in 1950 to see that the entire black sand which is available in Kerala seashore should be channelized to atomic energy. But the problem what we are facing at the moment is most of this monazite is now recovered by IREL, and they are trying to take out, this one, nuclear materials from that. Okay. So, and Atomic Minerals Concession Act, which has come in 2016, which resolves all B sand, deposit containing more than 0.75% of monazite to be only government-owned companies. This is where the problem lies. So nobody else can process monazite to recover, rare earth oxides. So whether it is for permanent magnets or it is for other applications, there is a dearth of input materials in the country. So we need to, come out. We need to find out a solution to circumvent this problem. By if you look at China, what China did is 863 program in 1986 for the new materials. They stopped supplying the critical materials like rare earth oxides to other countries. So until otherwise we initiate a new program to recover rare earth oxide to 3 to 4 N purity, because like that Cement Hyderabad is also a high purity laboratory. We have induction sound refining and all that. We all should work together to enhance the rare earth oxide production to the required purity. This is the first thing which we need to do.
Right.
I feel. Okay. So the second thing which I propose is that other than rare earth oxide production, like I can give you a case study. We are a small organization. Cement Hyderabad is only 38 permanent manpower. We produce the entire hafnium metal sponge required for the country. From zirconium raffinate waste which is coming from nuclear fuel complex. So we convert hafnium oxide into hafnium metal sponge. Okay, maybe the cost of production is slightly on the higher side, but in spite of the fact that we are able to do that. So we need to work together, we need to connect together, we need to make some framework wherein we should be able to scale up the technologies to the required level. Otherwise, as Sir has told, the industry representative has told, matching with the imported price will never be met. This is what I want to share with you. Thank you.
In addition, I would like to say that it's also very critical to achieve the purity of the rare earth oxide. If we can able to get it from NdFeB, we get a mixed rare earth oxide of Nd and Pi. So that again lowers down the price of the actual material if we go for a virgin Nd2O3 kind of material. So yeah, in terms of purity, I fully agree that because that will act as a benchmark for going for the even electrolysis. So first we need to ensure that such kind of purity can be reached even before going to the electrolysis of such salts. Yeah, that's all. Unless we are going for the preparation of a mixed metal alloys, that's altogether a different thing.
And also, maybe I would like to add some more point, like both from Dr. Ratish and Dr. Kalisinji, regarding the recycling, like where we are and whether the capacity building is sufficient to meet, because we are a very young economy with a very good buying power. So we are getting rare earth magnets in different sizes. So what about the recycling aspects, sir? Because like in batteries, that is going to be a issue sooner or later. Maybe you can just give us some inputs on that. Yeah, please, sir.
I can see that we are all working on a different platforms, but more or less there is an overlapping. Like Jaishankar was mentioning, Indo-Australian, now we are going to work. We got that ASRF around 14, so we'll be working with Australian universities now next 2 years on strategic minerals development, and that includes something very low grade ores and then recycling. The issue here is that many of the time in India, what I feel it is that this is my personal, maybe Ashwinji may correct it. The problem here is that the collection and then quantity of homogeneous material availability. But the first issue, when we want to go for a recycling, okay, I get a scrap from X industry, scrap from Y industry, even the black mass that is being produced is not having any, what to call it as a benchmark. And incidentally, I am also a part of the chairman for VA standards for aluminum. And then we are looking to make a standard for the scraps for obtaining. So we are finding it very difficult to get a consensus, because the issue here is that when you are talking about a scrap or a recycling, first is that what are we talking about the raw material? Raw material will have a different composition. A small packet of raw material coming with an iron in a non-iron matrix puts on a load of iron removal for the whole circuit. So I'm just giving an example. So the problem in India is the collection and the standard of was the scraps. So Niti Aayog and BIS are working on bringing in some kind of standards. Now we started 2 areas, copper and then copper bearing and aluminum bearing. And its discussions are going on. It will go for wide circulation shortly. So we will be getting a lot of this thing. The issue is the heterogeneity. Second is the supply chain. Okay, we have some material which we have done it. So who is going to supply it on a continuous scale for let us say 2-3 years? Third is the technology itself. Today we are talking about lithium-ion batteries recycling. You have whatever spent batteries available as of now, we would be having cobalt, because we also did projects of recovery of metals from spent lithium-ion batteries for Nissan cars when they went for hybrid cars and all those things. But the compositions are different from what they have that. And today we have been discussing with some vendors who are going to put up the battery industries in Tamil Nadu. So there's no cobalt. Now the cost of this thing is lithium. Now lithium is scarce but not expensive, except for these few after this war started, and then the prices of lithium carbonate has skyrocketed. Otherwise, it was all flat at the bottom. So it is critical for us, but not necessarily expensive material. So when we did recycling of lithium-ion batteries, the money was coming from cobalt, nickel, not from lithium per se. Now the scenario has changed. So I put an industry, let us take a developer technology. Tomorrow, after 2 years, the whole chemistry has changed. So there is a need for understanding and something where substantially we need to work on recycling. We need to see that what is the amount of the mass that is generated and at least available for next 5 years. And what should be the return on investment? If my planned payback period is 2 years, I should have at least that material issued from the raw material side. So this is the main critical component in industry. Otherwise, technologies can be developed. That's what my feeling as far as recycling is concerned. There should be a what to call it as some area it is developing, and like I said, BSF is going to make a standards for the scraps. But these things have to go, policy decisions have to be taken.
Dr. Ratish, can you please add, sir, some more, because CMT is also working on battery recycling.
I 100% agree with the comments from the previous speaker. See, we are talking about a purity of 99+% for a mixed rare earth oxide. Okay, so recovering individual rare earth oxides from small quantity of like mixed rare earth oxides is never economically viable. Okay, this has been debated at Niti Aayog level, and we have been asked to submit all these recovered materials to IREL for further recovery. These are all not pragmatic, so we need to have a consortium wherein all these mixed rare earth oxides are coming. I can give you an example, in PCB recycling, we produce, this black copper. So recovery of precious metal from black copper is a laborious process. It takes months together. Like what we thought was, instead of further recovery, we can channelize all these black copper to Hindalco kind of people who will further recover, these precious metals from that. Like that, we need to have separate entities wherein we are recovering mixed rare earth oxide, and further it is going to a centralized location like eco park concept. I would move to the idea of eco park concept in the country to amelioration of recovery of rare earth oxides, high purity rare earth oxide, and further utilization of same for magnet production. I think this is what I want to propose, because these are success models in China and Hong Kong, this eco park concept. Thank you.
Just to add, sir, I think IRL MD in some other interaction, he has told that they are going for ahead with, they are in the process of developing a rare earth research park and the titanium park at Bhopal. They have already, it was supposed to be thrown open. I think because of this COVID issue, there is some delay there. And they wanted to bring both the IRL production side with the industries. That is their plan. I think that is what they mentioned earlier in some other interaction. Just I wanted to add it. Sir, is there any other point we should discuss here?
I agree with Ratish, because what going up to that level is cumbersome. Even for fly ash, red mud, What our objective as per Niti Aayog is to get into the RE concentrate as much as possible. Don't go for separation chamber. There are BRC and IREL have that know-how, and because again, in industry going to that level is a difficult task. Maybe what is that these eco parks can do a heterogeneous raw materials, produce a kind of a concentrates, and leave it there for somebody else to go for high pool. Because that itself is a very cumbersome process, and you start going into totality, it may not be economical.
But sir, if you may agree that again it will come down to the same thing for the lithium-ion batteries. You will get different grade of a mixed rare oxide, and again you have to
no,
set
that
the
specifications
benchmark
are
for.
made. That's what I'm saying. When we are making aluminum scrap, it's not like that we are not taking. So there are 10, 20, 30 items have been listed. Now, when the scrap goes for melting furnaces rules, then there is a language. Melting furnace output is a standard. So when you do it, up processing is this much is acceptable. So which is an input for the downstream process who have the technologies for further upgrade. No, you don't. You have starting from ND separation will take about 90 series. I mean, who will invest it into that kind of solvent extraction? This thing. So there should be there something. But let us say the ND concentrate comes with this impurities acceptable for my plant. It's okay.
And in India, there is only one single plant which does solvent extraction is Nicomet, which is now evidently is a part of a Vedanta. So no more the
no that
company.
That is for the nickel, but IREL has the S6 plants and IX plants also there. They have that facilities also there. What happens is they are.
But on a commercial scale.
Yeah, probably they are not doing it on the secondary resources or secondary that part I'm saying. So if not IREL, somebody will.
I think IREL also has its own mandate to valorize Indian rare earth resources. So I think they will be already focusing only on that. That's what.
Yeah, now they are, to the best of my knowledge, right now they are going to the production of only NdPr, because that's what is being sold. And we are talking about NdPr, that once it is the ratio is then, you're not going to talk about the separation of ND. They have the facility, you have ion exchange results and all. But market, it's a driven, it's an industry. They look for the profits. Wherever return of investment is high and saleable, they will stop.
I think before we close, maybe you can throw some light on this extraction of rare earth from red mud and also from fly ash. I mean, where are we? What is the future vision? I mean,
as per Niti Aayog, we have been given two tasks. One is there are two committees. One is the red mud, where like I showed you that we joined three organizations, R&D organizations, and three industries, prominent industries, aluminum industries. So different flow sheets are being developed. Basically, it's complete holistic utilization. Today, when we're talking about a waste material, nobody is interested to generate another waste out of it. So when we want to use a red mud or a fly ash, the first important criteria, point one, is that whole mass utilization. You're not going to create more residues or effluents, which will be further problem. Point one. Point two, the rare earths can be only tapped when you start concentrating into the downstream, taking out the major mass. So both the processes are addressed in attacking first the major mass. So as far as fly ash is concerned, we have a patented process up to the concentrates. We could get scandium, even whatever I showed the 100. We have even achieved 300 ppm of scandium and more than 1,000 in a small scale. And then it's proven that we could concentrate using a chemical method. The rare earths can be concentrated in one pocket, which further need to be pilot scale tested, because we need a large mass of this concentrate to further develop the downstream process. That step is what you are not actually going for an individual rare earths. This iron hydroxide is basically 99%. We are talking about 400 ppm to 3000 ppm. Still, we are talking about ppms. So further, we need to separate the iron hydroxide and then get the concentrate, which is having as mostly mixed oxides. That will be the raw material for further separation. Why would I go below that? Because those technologies are available. So to one step ahead.
But on that point, with respect to the comments made by Jai Kumar sir, if I say effectively the concentration of these metals are in the range of, let's say, if I assume that's 1,000 milligram per kg. So for a ton, you have a 1 kg. So effectively, you are not getting a very high pure mix RE oxide so as to claim the price of 5,000 or 6,000 rupees. So it's as Sir rightly said, that has to be offset by the value-added products that we are getting from the processing of, let's say, titania or alumina or silica and iron oxide. It has to be offset by such kind of other value-added product, and if you are able to get the desired purity and the desired rate. So yeah, so
that I
getting
agree.
such kind of purity.
I agree, Shivendra. That's exactly. So without even iron hydroxide considering the valuation of the rare earths, the other process should be economical buyer. At least that is a zero cost. So valuation will only come from the rare earth further process, but rare earth itself per se will not be giving a total economics to it. So it will be
Right,
the other
because
parts.
effectively you have a total, even if you can recover the complete rare earth with a 99 or 99.9% recovery, you will only be able to get a 1 kg of material by processing 1 ton. So for one ton, you have a multiple stages you require on a practical scale. So this has to be, the capital cost and the OPEX cost has to be offset by the other valuable product, which again has to be benchmarked with the industrial kind of products that we have. So certainly these are the important considerations.
Roughly calculated,
My understanding
around 4 to 5 years is the return on investment based on that RE concentrate. Now that minus RE value as a pure oxide. So that itself
Right.
flow sheet. So we have some nominal value for that RE concentrate, which is not at all the actual value of oxide. So further, when you do this processing, it will add to the cost and also economics. That is a
and again water cost, and again that type of multiple stage separation may again add up the other values to it.
I think we have any other points to discuss, sir? I think it was a very fruitful, long discussion among all the partners. So, is there any other point should we discuss, sir? I mean,
Yeah, Jaykumar, I have some small point to just add to Kali Sanjay sir about the red mud. Sir, in the red mud, what we found the titanium oxide presence is also very important because I found that some of the red mud from Indalco, so there already the titanium is present more than 10%, and some of our enrichment studies we found it is enhanced to up to 25 to 30. As far the NIS concern, so we have the technology for making the synthetic rutile. So it was demonstrated in pilot scale studies. So maybe in future, some of these activities can be clubbed to us, and we can also be part of this particular this where we have developed the process in pilot scale, especially for the titanium oxide aspects. So just I want to add on this your red mud value addition. So thank you.
Jaishankar, I agree about because we are aware of this. These all things have been studied before this one. NIST has the process of rutile and this one. And Garuda Chemicals also did it. Even if you are remembering it, they have done even a pilot scale. But in this process, what is being done is that the major mass of alumina iron is removed, and then you have a concentrate which is containing both NML process and say IMT, because it's a combined process basically. Some of the material that we produce actually will go to NML for the pig iron production. So in there we have a concentrate which is coming at with titania as well as RE. That's a very low concentrate. It's a completely different material. It's a chemical, chemical process material. So it's a different. Definitely, if there is a requirement, we'll definitely, when we come to that stage, we are there. So when we reach there, definitely. Even Jaishankar, I've been talking for ND. Once we get that opening and all those things, we'll definitely take all of your help, and then it's required. Why would we do a reinventing of the wheel? We have that facilities and expertise within ourselves. Sure.
Thank you very much.
Thank you.
I think in the event of no further points, I think we have had a very fruitful and long discussion among all the stakeholders here. And I thank myself personally, Mr. Vikram Dut from Ashwini Magazine for joining us. They are one of the industrial leaders in magnetic production in India. And I also thank Dr. Ratish and Dr. Rambabu from Siemens Hyderabad, and our sister labs, Dr. Kali Sanjay from IMMT, and Dr. Jayshankar and Dr. Shivendra Singha, for all your time and spending half of a day. And it was a very, hope it is a very fruitful initiation, and hope we will all work together. So maybe sometimes so that wherein we will have a overall the value chain starting from an Indian ore to a Indian product, maybe metal or alloy, and subsequently also for the recycling for the Indian produced rare earth magnets. Maybe down the line in 5 years or 10 years, we will have an entire value chain being addressed at the CSIR at a pan level in line with the industrial expectations also. Wherein, as you have also rightly mentioned, like Niti Aayog is having a very sincere, serious effort to have a what you can say the benchmarking of the scrap for magnets. Wherein, like in the case of lead acid battery, we will also have standards being developed. Subsequently, that will be also addressed because already you will be having both at IMMT and CMET. There is already a flow sheet which is developed and tech transfer has already happened with IP production. So subsequently, that will be all met subsequently in the future also. So hope this initiation during this 75th year of our independence, and also we are happy that this is also the 75th year of foundation of CSR Sikri and the 88th year of our CSR system itself. So this all will happen somewhere. Hope this meeting happens to be one of the initial stages of this effort in this direction. So we personally, I thank on the part of the organization committee for this iConnect meeting. Myself and Dr. Nimisha from engineering, we thank you for your time, effort, and the fruitful discussion. Thanks to you. Thanks to everybody, sir. Thank you. Thank you. Thank you.
Thank you.
Thank you, sir.
Thank you. Thank you, sir.
Thank you. Thank you. Thank you. See you all, sir. Take care. Thank you.
How's your health, Sanjay, sir?
Thank you. Thank you, sir. Thank you.
Yeah, sure.